paste. Okay, just
yeah. I'll paste it so that so the same channel link.
huh. Okay, so YouTube.
Let me just copy paste the channel link here. So chat. How do I do a chat? Yeah. Here is a chat. Let me just copy. I'm pasting the chat here.
Now I can also see the feeds in the YouTube channel.
Okay.
Oh yes, people are also watching it.
Okay. Okay. So then we are gold. So I mean, the only thing is that I'll send to all the panelists. I'll send the CSC login and the password.
Okay, sure. And Anirban, I think you only had the credentials to make anyone as a co-host. I cannot make anyone co-host.
Acha. Okay. But you started today, and you were the host.
Yes. So if I start, then I am the host. But like I have transferred you the thing.
So let me transfer you the.
Okay.
Oh no. Make host. So make host. Okay. So if I leave, host to answer. Yes. Okay.
Yes.
So now you are the host. Okay. Okay, then looks good. So okay. So one thing is that I mean we had promised the speakers that we'll send a 1 hour reminder. So I guess the session volunteer can possibly send the emails to them.
Yes.
I mean, I guess one email to all the panelists together in the session will be fine. Okay.
Yes. Okay. All the best.
Okay. Bye. All the best. Yeah.
So Mayank.
Yes. Okay.
So Arup wants to test the screen share once. He's the first one to go. Can he join now?
Yes. He can join now. Yes.
Okay. So he wants the. Okay.
So he has got the link, right? Udit?
I have to send him again. So which one? Arup.
No. So Arup has got, I think, one email in his account only directly. So that went from Zoom.
That is for panelists, right?
That is for the panelist. Yes. Oh, okay. Udit, so you will be able to do that, right?
Yeah, I mean, all I have to do is just check whether screen is sharing and.
Yes. And the audio and video is coming. That's all.
Yeah.
Okay. Good. So Udit, I will join it around 8.
Sure.
Okay.
Hello?
Hello, can you hear me?
Yes, Arup, I can hear you. I can see you.
Nice. Let me see if I can. Can you see my screen?
Yes, I can.
1 second. Can you see the full screen now?
Yes, I can.
Okay. Then are we all set?
Can you just try to change the slides?
Yeah.
Yes, slides are also changing well.
Good. So you're all set?
Yes, thank you.
So I'm leaving now, right? I'll join back, or should I just keep it on?
Maybe you can join back later. Still, there is some time.
Okay.
Yeah.
Man, just one thing. Hello.
Okay. Do we start in 3 minutes?
Yes, yes, we are going to start in 3 minutes.
Sure. Very good. So the YouTube link is not there in the web page. Can Shruti, can you put it in the web page? YouTube link.
Yes, sir. I will add that.
Mhm.
Mayank, your voice is very feeble. Can you say hi, hello once more?
So is it audible, clearly audible or not?
Yeah, better.
Okay.
Maybe when you are speaking, make the computer audio full volume. Then you can reduce again.
Okay.
Everything is going to YouTube live here. Anyway.
So am I audible now clearly? Can one of you please confirm?
A little feeble.
Yeah, a little feeble. Maybe coming a bit closer makes it.
Okay. So maybe you can confirm now also, that is also fine. Yes, I'm now very close to the screen.
Yes, it is much better.
Okay. So let us wait for 1 more minute and then we can go ahead. So a very good morning to all the speakers, attendees, my colleagues and my dear students. So I warmly welcome you to the first edition of the Indian Symposium of Machine Learning in short, this IndoML 2020. So this event is co-organized by a team of researchers who are from Computer Science Department from IIT Gandhinagar and IIT Kharagpur. And I believe this is the first virtual event which has been co-organized by IIT Gandhinagar and IIT Kharagpur in general also. So this event spans for 3 days, starting from today, December 16, and we are going to have a lot of exciting talks in the next 3 days. So till December 18, 2020. So in contrast to many other parallel virtual events that are happening across the globe as well as or in India, there is a kind of a very distinct pattern. So they are kind of more specific to computer science, where they are kind of talking about how AI is impacting some fields in computer science, or like the different fields of computer science, are kind of enhancing the what research has been done in AI. But IndoML is something which is kind of very different. So we define IndoML as more general platform where we discuss AI and its impact to the society in general. And we have keep this year's theme as AI for science and science for AI. Right. So it encompasses almost everything where AI is impacting different fields of science, and different fields of science are impacting AI, and how both of them are kind of enhancing each other's. So this year theme, like according to this year's themes, the entire the talks are broadly categorized into 3 categories: chemical and atmospheric sciences. So that's one theme. The second theme is physical and mathematical sciences, and the third theme is social sciences. And we have tried to pull in a very diverse line of speakers across these 3 main broad fields. So we have around 21 speakers, and these 21 speakers represents around 4 continents. And they represents academia, industry, as well as the social sector. And it is not just that the current the IndoML is kind of a symposium which is just restricted to computer scientists. It is again the speakers are some of the speakers are mathematicians, some of them are computer scientists, of course, some of them are physicists, biologists, geologists, and even some of them are social scientists too. Right. So it's not just it is about for computer scientists. So these are some of the speakers who shall be talking about some topics in chemical and atmospheric sciences. So we have 8 speakers in line who shall be talking around chemical and atmospheric sciences. And then we have 7 speakers who shall be talking about physical and mathematical sciences. So more about physics and mathematics, how it is impacting AI, how AI is impacting these fields will be talked about here. And finally, we have the third broad field of research, and that's social sciences. So in social sciences, we have 6 speakers. And again, we shall be talking about the connection of AI with social sciences in all of these different talks. And it is not just that we have just the diversity in the speakers. We also have a huge diversity in the audience too, right? So we have got more than 2,700 registrations, but majority of them are from India. Almost 90% of them are India, but it also includes some other countries. Like for example, we have some registration from USA, we have some registrations from UK, Germany, China, and so on and so forth. And we also have a very a few registrations from South Africa. So that's kind of very unique to this kind of conference. And again, as I said before, there's a huge diversity in audience. So we have an audience in 2 broad categories. Like we have students as well as we have working professionals. So among students, we have undergraduates, we have masters, we have PhD students, and among among working professionals, we have postdoctoral researchers researching in different fields of science. We have academicians who are some of them are junior level faculties at state or central universities, some are senior level faculties at central or the state universities, and then finally we have a lot of registration from the industry professionals. And this is who we are. So we are a team of 6 people who are organizing this entire conference. So Professor Nilay Ganguly, who belongs to Computer Science Department in IIT KGP, Dr. Anirban Das Gupta, who is from CSE IIT Gandhinagar. We have Dr. Animesh Mukherjee, who is again from CSE IIT KGP. We have Dr. Udit Bhatia, who is from Civil Engineering Department in IIT Gandhinagar. Then it is me, Mayank Singh, Computer Science Department, IIT Gandhinagar. And then we have Raj Sharma, who is head of operations in Videocon. So again, Raj has been like phenomenal in attracting and publicizing this event to a very, very large audience. So we are very thankful to Raj. And no conference or no activity is just belong to, or like is only possible by the organizers, right? There are foot soldiers, there are a set of dedicated volunteers. We too have a huge a set of very good set of dedicated volunteers. And in this IndoML conference has been organized with the help of these dedicated volunteers. So we have 8 volunteers: Shruti, Somadeep, Rachit, Supratim, Gaurav, Arijit, Avirup, and Abhishek. And many of them might have already contacted you. Maybe they have given you some registration related help or Zoom link related help and so on and so forth. So in future also, like in next 3 days, if you feel any difficulty, either it is technical or you are not able to do something, you are not able to post your questions, just feel free to contact them. Their email IDs and other things are already with you. So you are already in the some of the conversational groups like WhatsApp and like you have been sent some email. So feel free to contact any one of them. And at the last, but not least, we would like to have like to have a very special thanks to the AI journal. So the journal has sponsored this event, and we are very, very thankful to the artificial intelligence journal. Okay, so next moving to the plan and next moving to the program that we are going to cover in next 3 days. So let us have a very brief glance to different sessions. So today is the day one, and we are going to have the session one just after this brief talk. And this session is about chemical and atmospheric sciences. So we are going to have 4 talks in this session, and in the next session we are going to have. So this is the first session, and this is the first session, and in the next session, like today itself, the day one, session 2, we are going to have again 4 talks which are about physical and mathematical sciences. So we'll be talking mostly about how physics is impacting AI and like how like mathematics is kind of impacting AI and vice versa. Again, tomorrow in the first session, we'll be talking about social sciences. So like how social sciences is again connected with AI and how both of them are kind of impacting each other. Tomorrow in the second session, we will be talking about chemical and atmospheric sciences. So we shall be talking about, we are going to have 4 sessions or like 4 talks about chemical and atmospheric sciences in day 2, session 2. And on 18th, the day 3, in the first session, we are going to have 3 talks. We are going to have 3 talks, and these talks again are in the broad category of physical and mathematical sciences. And finally, we conclude in our last session, that is on day 3, session 2, and this session is devoted to social sciences. So we are going to have 3 talks in this session. Okay, so let's begin with today's session, and this session will be, so there will be the first talk in this session by Professor Arup Ganguly, and the topic for this talk is AI the new electricity that will transform Earth system sciences and engineering? So Professor Arup Ganguly is a professor of civil and environmental engineering, as well as the affiliate professor of both the Crowley College of Computer Science and the School of Public Policy and Urban Affairs at Northeastern University in Boston. His research and teaching interests intersect water sustainability, climate science, urban sustainability, and infrastructure resilience, as well as the machine learning and nonlinear dynamics. He is a fellow of American Society of Civil Engineers and a senior member of the Institute of Electrical and Electronics Engineering. Prior to Northeastern, he was employed with US DOE's Oak Ridge National Laboratory, and before that at Oracle Corporation. So Arup Ganguly has published in journals such as Nature and PNAS, besides other journals across disciplines in geosciences, engineering, physics, and data sciences, and written a textbook on critical infrastructure resilience, and won best paper awards in top tier AI conferences. So he is a co-founder of Boston-based climate startup Risk, and where he remains the chief scientific advisor. Ganguly has a PhD from MIT, Cambridge, and a BTech from Indian Institute of Technology, Kharagpur, India. Over to you, Professor Ganguly.
Thank you very much, Mayank. That was a kind introduction. Let me see if I can, if you let me share the screen. Yes.
Yes. Please go ahead.
Give me 1 second. Can you see my screen?
Yes, it is visible. Yes, please go ahead.
Okay. So again, thank you so much. It's a pleasure to talk here, and pleasure also to see some familiar faces. Sorry, let me just go back. So yes, my tongue-in-cheek title of this presentation is Artificial Intelligence, the New Electricity, that will transform the Earth system sciences and engineering. So let's start. This is Stephen Hawking. And this great physicist, he felt that development of AI could spell the end of the human race. This is Bill Gates, and he felt that it's just like nuclear bombs and nuclear technology. We shouldn't panic about it. We should just use it right. This is Andrew Ng, and he says he compares AI to electricity. Just as electricity transformed everything 100 years ago, today it will transform all industries. This is, I don't need to say who this is to an Indian audience, Sundar Pichai, CEO of Google, and he says AI is more profound than electricity or fire. So with all this, what I was trying to see is, in this introductory talk, is where are we? And coming a little bit back to reality, this is Michael I. Jordan, currently professor at Berkeley in computer science and statistics, one of the top pioneers of what is now called machine learning or AI. And in his view, the revolution hasn't really happened yet. In fact, he says that, this is, we are looking at creation of a new branch of engineering, much like civil engineering and chemical engineering in decades past. That's his words. And he's saying ideas such as information, algorithm, data, uncertainty, computing, inference, optimization, all of these are building blocks. And these will interact in various ways to solve societal scale problems. He also spoke about, just as when civil engineering started decades back, centuries back, we may have been a bit careful about, okay, should I enter this building? Should I go on this bridge because it might break? That's typically not how we feel these days when we enter a building or try to cross most bridges across the world. We don't feel like it's going to break. Buildings, bridges, and dams, reservoirs do break often. In the US, there's an example of Hurricane Katrina where a levee broke, leading to chaos and significant damage in the iconic city of New Orleans. These things do happen, but that's not an expectation anymore. The field has matured. And what Professor Michael Jordan is saying here is that artificial intelligence as a field needs to mature even further. So here is Gartner Group. Gartner is one of the most respected groups which sort of evaluate businesses. And this is their expectation. This is their hype cycle. They have this thing called hype cycle where they feel that every innovation, emerging technology starts with a trigger, goes through a peak of inflated expectations where we think that that technology can solve everything. And then we sort of realize that, well, it doesn't solve everything as we thought. That's the trough of disillusionment. And then there's the slope of enlightenment when we think that, well, we sort of understand that these are things it can solve and these are things it cannot. And once we do that, then we finally reach the plateau of productivity for that particular technology when we understand where it works, where it doesn't, and then it starts to be really useful. So some things like explainable AI, which was there in 2019, in 2020 that persists. And similarly, some things like generative adversarial networks, GANs, as they're called to a machine learning audience, they sort of remain at the same level where they were. There are some other technologies that have come here, and some things, of course, related to COVID, such as social distancing. But many other things, broadly the AI theme, you see transfer learning here, you see knowledge graphs, you see adaptive machine learning, responsible AI. So in a broad definition of AI in the technology space, that seems to dominate at least the hype cycles, as Gartner calls it. Coming back to Jordan, Professor Jordan, so he says that there's a need to go deeper. This deployment of deep learning infrastructure is somewhat narrowly defined, and he highlights things like explanatory principles, meaning and reasoning, causality, uncertainty, develop systems that can actually solve real problems. So he talks about things that still need to be done and this need to understand what we are trying to do with AI. And he says that unfortunately AI has become a buzzword, what he calls an intellectual wild card. So much so that it's hard to even know what AI is these days. Some people would do linear regression and call it AI. Some people would do game theory. Some people would do machine learning. Mostly the current state of AI is we probably owe it to the developments in machine learning. And then he talks about data science, this phrase that has been gaining momentum, which is machine learning algorithms and partnering in partnership with database distributed system experts to solve real problems. So here is one journal. This journal, by the way, in the machine learning community is not looked upon as much as we would think it could be, simply because it's behind a paywall, and that's not usually how machine learning operates. But be that as it may, just taking some of the broad definitions of artificial intelligence, or what they call machine intelligence, they talk about AI, robotics, they talk about machine learning, including deep learning, neural networks, symbolic reasoning, genetic computing, neuro-inspired computing, agent-based systems, cognitive computing, robotics, etc. So all of these, they sort of put under the broad umbrella of AI. And if you think about how AI has evolved, AI has incidentally gone through what I call a karmic cycle, this eternal life and death cycles. It sort of comes back and then it goes into oblivion, or what are called AI winters, and then it has a tendency of coming back again. So I'll not go through each of these. Some of you know these, some of you can find out, but the basic connectionist architectures, those were proposed all the way back in 1940s, and then there are various algorithms proposed for using them in various ways, and then certain tricks and so on. It went through various AI winters. It went through various cycles. Neural networks used to be a big craze at some point, and then there was some other point when neural networks were just not used by anybody, till certain kinds of neural networks, some of which we now call deep learning, deep networks, they came to the fore, and they seem to outperform many other methods. And that's what caused, first neural networks, then through that machine learning, and through that the whole field of AI to again get into prominence. So these cycles have gone on for a while. And some of us who have followed these cycles in some way, from both methodology and then applied point of view, for example, in hydrology or atmospheric sciences or infrastructures, we have had to follow many of these cycles. Where are we right now? So these, first of all, in terms of the theory that has evolved, this is 1989, when a couple of theoretical advances happened simultaneously. Basically, what Hornick et al. And Sibenko showed independently is that multi-layer feed-forward networks, what we call artificial neural networks, or superposition of certain kinds of functions, such as sigmoidal functions, can act as universal approximators. They are universal function approximators. Now, this may seem like a big deal, but it has to be put in context. If we remember that polynomials are universal function approximators, as are Fourier series. But at least there was this theory that, well, neural networks seem to be working well in some cases, maybe not so much in some others. But why are they working? So typically, often in computer science, machine learning, things have worked first, and then the theory has followed. So this was that theory that said, okay, at least they do act as universal function approximators. And then this was followed by, this developments in deep learning, as I was saying, and these three gentlemen, they won the Turing Award for advances in deep learning, and these are the kind of things that got both, neural networks, and through it, machine learning and artificial intelligence back into the mainstream, if you will. And in terms of understanding why they work, what are the kind of things we talk about, bias variance trade-off that we have talked about in general in statistics. We talk about model complexity and model parsimony, we have this basic scientific principle called Occam's razor, where the broad idea is that we should always go for the model which explains all the data, but among all the models which explain all the data, we should go for the simplest one. So that's the broad statement of that Occam's razor principle. And one of the ways in which we examine that is through bias variance trade-offs, as they are called. How well is the model handling the basic signal, and how well is the model, how is the model performing in terms of variability along these signals? There is often a trade-off there. So people have tried to examine neural networks which have input layers, hidden layers, output layers in variety of ways. These have various weights and nodes. And in these artificial neural networks, which were developed around this version of it, which was further developed, I would say, around 1990s. Remember, connectionist architecture started around 1940s in a serious way. But then people started to think about how to impose Occam's razor principles, how to impose model parsimony, not make the model too complex, because too complex models may fit a function but may not generalize well. There are a lot of debates back and forth. David MacKay, who was a very well-known name, the late Dr. David MacKay, he was also at some point the chief scientist of the United Kingdom. So he was a big proponent of the use of Occam's razor in the context of artificial neural networks, what would now be called shallow neural networks, in the sense they were not as deep as they are now. And there were some arguments back and forth. I mean, another very well-known Bayesian neural network scientist, Radford Neal from Canada, he said that why impose a limit on complexity? And David MacKay's answer to that was, you don't need to explicitly impose Occam's razor, but if you do your Bayesian modeling right, then it's automatically imposed. So from there, I mean, shallow neural networks were already fairly complex. And from there now, we have now gone boldly into this area of deep neural networks, which have, if you think of number of parameters and things like that, and potential complexity of this model, potentially the hypothesis space it can explore, it's tremendous, right? It's something that from an applied statistician perspective might boggle the mind, that how can we use something that's so complex? But then people have started to explain and explore these. I wouldn't say the explanation is perfect yet. Part of it is still something like a black box, gray box, but we are getting better at that. So some of these explanations, this comes from a recent PNAS paper, which I'll talk about eventually. But people have tried to explain what these networks mean and how how we can use them. And then there have been these developments around uncertainty in these neural networks, some sort of Bayesian deep learning, development of Bayesian approaches, or at least approaches motivated from Bayesian algorithms to try and understand uncertainty, to try and look at ensembles of these neural networks selected in a certain way. So there are various ways of implementing Bayesian schemes. So in a sense, we are going back to that old, the world of David MacKay and Radford Neal, but in a slightly different way with these deep neural networks now. In terms of understanding these, there have been some bold theory, or at least going towards theory, such as are there regimes where deep learning versus shallow learning works better than the other? So as we go deeper, in the sense of as we have more hidden layers, larger number of weights, larger width of these networks, meaning larger nodes within one layer and more hidden layers, then maybe what we do is we sort of go towards that ideal of universal function approximator a bit more. But if we overdo it, we maybe lose model parsimony, the whole Occam's razor principles. Is there a balance between that? Is there some sort of learning and what has been called information bottleneck principle? Why these approaches work? And I think in this workshop later, we'll hear more from various experts about the latest and greatest in our understanding. What seems clear, though, is that there are certain areas ranging from computer vision to machine translation, and also many other areas, including these days weather forecasting, or at least certain aspects of weather forecasting where they do seem to work fairly well. In fact, better than uh, better than the state of the art, at least in some cases. Here are two articles, one of which appeared in PNAS on the left and another in Nature Neuroscience on the right. And these articles appeared this year. So in a sense, these could be considered the current state of our understanding. On the left, they talk about unreasonable effectiveness of deep learning in artificial intelligence. So these are high dimensional systems. They have certain special mathematical properties that we're only beginning to understand. That's the view of this article, which by the way is fairly positive, fairly upbeat about deep learning, but just says that we know that it works across a variety of applications. We just don't know the why. I mean, it's not that we don't know the why at all, but there are many gaps in our understanding. And on the right, there is I talked about the three gentlemen who won the Turing Award. The senior most researcher there is Jeffrey Hinton, who is the last author on the paper on the right. He talks about back propagation, which is one of the most commonly used algorithms to train or for the neural network to learn, and has been used for a while in a variety of formats. And this is a comparison of, does this really model the brain? Neural networks at some point was at least motivated by what used to be our understanding of how the brain works. And we have gone back and forth. I mean, we currently, I think I can say with maybe some degree of boldness that we do not understand really how the brain works. We are trying to understand that, and relating how neural networks work with the brain is still a bit premature. And sort of, this article says that when we compare backpropagation with the brain, historically, it has been viewed as biologically problematic. But well, there are some recent developments which we need to look at further. So that's the state of neural networks, machine learning in general. What does all these things mean for Earth system science and Earth systems engineering? So in general, if we look on the left, that's what Earth system science is the most, currently, when you think of Earth system sciences, we think of physics and biogeochemistry. We think of models which require high performance computing, and some of the largest supercomputers in the world are used to run these Earth system models. These used to be called general circulation models at some point, then global climate models, and now they are called Earth system models because they model or at least attempt to model all components of the Earth system. Through physics, chemistry, biogeochemistry, etc. So that's the state of the art. Now, on the right, this is a paper. This is a figure from a paper in Nature, which talks about how artificial intelligence is starting to make some difference in this field. And they talk about, specifically, this Nature article talks about deep learning and process understanding. And here they give 4 examples of some breakthroughs in deep learning and how they have been impacting or started to impact. These are very emerging areas, by the way, how they have started to impact problems or applications in Earth system science. The second one of these 4 examples that they have selected, the second one is one of ours, which talk about use of computer vision, use of deep learning in the context of image and video processing, so broadly computer vision, how that can be used for statistical downscaling, which is this process in which the low resolution simulations from these Earth system models can be transformed into higher resolution outputs, which are then useful, which then can become useful for stakeholders. So in trying to build these, this was a collaboration with NASA and with a startup company, Risk, which is a spin out from our lab here. And as I was saying, this use deep learning, first of all, more as a demonstration than anything else, that this process of statistical downscaling can be thought of as an image processing problem. And so that's all that this first paper was, and it got an award, etc. In KDD because it was one of the first demonstrations. At this stage, I would think that there are other, I mean, other lines of work which have expanded on it, including a line of work by Professor Udit Bhatia and his student Nithin Hiralal at IIT Gandhinagar, and several others. But one other thing that, I mean, one extension of this was in the context of Bayesian deep learning. So this first article was in KDD 2017, which is one of the top machine learning data science conferences, and computer scientists, as we know, go by their conferences. Anyway, and then in 2018, there was a Bayesian deep learning version of that. I mean, all of this work was led by Thomas Vendal, my former PhD student, who is now at NASA, and this work was joined with NASA. So what this Bayesian deep learning did was trying to extend some of the concepts into data that can no longer be assumed to be Gaussian or, and have fairly skewed distributions. Of course, there are many things that still remains to be done in the context of climate. So for example, and one of the major hurdles is in the context of climate, we're talking about change. We're talking about fundamental change to the Earth's radiative balance. So we are not expecting a situation because of climate change where the laws of physics change. So we are not suddenly going to be in an Einsteinian, frame of reference instead of a Newtonian frame. So fluid dynamical equations and those kind of first principles based physics, Newtonian physics, is going to remain. And the Earth is also not going to become like Mars or Venus all of a sudden. But what can change are things like, if we are in Boston, that might begin to look like North Carolina, and there can be similar examples in India and across the world. So things might change in that way. And as things change, the first principles-based physics might remain similar, but some of the parameterizations or some of the statistical methods, including machine learning methods, question is, will they remain invariant, if you will, or to what extent will they remain similar, or will those function approximations hold as conditions change? So those are the kind of things. These are open challenges in these areas. Not to say that there is, some people have started to look at these areas, but these are fairly complex areas. One other thing that we have been looking at, and this is with my current PhD student Nishant Yadav, and with a scientist at MIT. I think you'll hear from him next. His name is Sai Ravella. So what we have started to look at, and this is a field that many others in climate are starting to look at, is in addition to looking at machine learning, which can be applied on the outputs of simulations or the residuals that we get when we compare, after comparing simulations with observations, can we use machine learning also to improve parameters within those models themselves? So this work that I'm showing here is just a very first cut, if you will, where we are using certain kinds of Lorentz systems, nonlinear dynamical equations, as a proof of concept to see if this can be done and how some deep learning methods compare with other standard Bayesian methods and things like Gaussian processes, etc., in the context of parameter estimation for these Earth system models. We talk about use of in Earth system models. I mean, we have a lot of physics that have been built over, and by physics, by the way, I mean physics, chemistry, biology. So science, a lot of science that exists which have been built over ages, decades, sometimes even centuries. We don't want to get rid of all of that and suddenly say that we want to represent everything with deep learning or whatever data-driven methods. For one that makes the task of deep learning or machine learning, whatever methods we are using, incredibly complex. So if we have some science, why not use that? And as some people say, when we think about physics equations, they are a sort of, they are a representation of what we know in some lower dimensional manifold, if you will, versus the data exists in a higher dimensional manifold, and there are trade-offs to using one versus the other. This example that I'm showing is, is one where we used physics-guided approaches to look at uncertainty quantification in climate. So this is Bayesian uncertainty quantification with physics guidance. And we have used that in the context of also physics guided machine learning for regression and also to improve physics with machine learning, which is some of the examples I showed. By the way, the uncertainties in climate are large. And so this is uncertainty in hydrology. This is P minus E, precipitation minus evaporation. At the top left 6 figures, which are not shaded, these show the simulations 30 years later of how the state of hydrology might look like in, with different models and with different initial conditions. And as you can see, they look very, very different. Now, if we look at the mean of all of these, multi-model ensemble mean, they are called, the average of all of these, and that's what shows, I show the average of all of these ensembles is shown in the bottom right. The change doesn't seem to be as much. Now, one thing to highlight there, though, is that we cannot design based on the mean. That would be like designing a bridge based on mean traffic, or designing a building based on, or a water tank based on mean level of water. So it will break. So we have to consider this entire plausible futures that can happen that climate models are suggesting. With all its uncertainty, in a field as complex as climate, we will have uncertainty. We need to characterize this and then base our design and operations based on that. And in addition to climate models, when you think about climate risk management, the figure on the left comes from IPCC. We talk about disaster risk. We talk about weather and climate events such as a Hurricane Katrina. I mean, in India, it would be called cyclones. So they hit, but when Hurricane Katrina hit New Orleans, and all of us may be aware of that phenomenon, New Orleans hasn't recovered yet. But one thing that happened is the hurricane came, it was an intense hurricane. We might be seeing more of those hurricanes in this era of climate change and variability. But also, there was an infrastructure with which the American Society of Civil Engineers had been giving a grade of D-. There was a levee that broke. And major flooding happened because that levee broke. And a lot of the assets and people were impacted because the most vulnerable people were the most exposed. Some of them were living below sea level. So there is a wide suite of models which can handle each and every aspect of this, whether it's looking at greenhouse gas emissions and land use change, whether it's looking at what we can do in terms of weather impacts, whether it's looking at risk quantification, whether it's looking at, in this case, flood or droughts risk management, or in the context of climate adaptation. There are a variety of models, simulations, data systems that can look at that. And each of these models can benefit through data sciences and artificial intelligence. And these include Earth system model components such as hydrology models. And as we think about those, we have to go fairly deep into how these models work. And this deep is not deep learning. This deep is deep into the understanding of the physical and biogeochemical processes. And once we do, and once we understand what are based on first principles and what are parameterizations that were built when we did not have as much data as we do now, what the trade-offs are and where some of the improvements could be. So, just to highlight, there's a lot of uncertainties just as there is a signal. So the signal exists in terms of climate, especially when you think about regional assessments, but also there is a lot of variability, and some of this uncertainty, some of this variability is because of gaps in our knowledge, but there is some uncertainty which is just the intrinsic variability of the system. So we have to design around that. There is no way that we'll reduce this uncertainty too much. And this goes back to things like chaos theory in nonlinear dynamics, among one. There are other kinds of uncertainties as well. One thing that nonlinear physics-based insights can do is give us some scientific advances in areas where physics models may not have done so well. So these include things like cloud physics. These include things like teleconnections. Teleconnections are when some weather or climate phenomena happening in one part of the world impact certain regional climate or weather phenomena in other parts of the world. There are causal drivers for why that happens, just that we may not understand all of this well. So one of those examples is El Nino. El Nino is a pattern that happens somewhere in the Eastern Pacific, but then ends up impacting tropical hydrology and in general hydrology the world over, and weather patterns the world over. So there are things there that we could understand with tools such as nonlinear dynamics and with data-driven sciences combined with with physics. So for example, we have used things like machine learning, things like spatial versions of complex networks, things like sparse group lasso, some in our lab, some in collaborations with experts in machine learning, such as some of these this work, the work on the left was in our lab, the work on the right was in our lab, but together with uh, Professor Nitesh Chawla from University of Notre Dame, who is a well-known machine learning expert, and the other work was led by uh, Professor Arindam Banerjee, who is at Minnesota and has now moved to Urbana. And some of these things, sometimes it's interesting that we can just look at these data sets, this vast amount of data sets, and if we cast our hypotheses right, if we understand the physics and the processes well enough to define hypothesis guided studies, we can get very interesting results about things such as heat waves. In a climate change context, what might happen to heat waves? They might grow worse, but the uncertainties and geographic variabilities may continue to exist. And things like cold snaps. So although overall we are looking at global warming, when we think about the extremes, the tails, they may not always exactly follow the means. So we might be in a world where heat waves grow much worse than they are with various levels of uncertainty, but cold snaps continue to persist in some parts of the world and at some times. We have looked at similar things in India and across the world, such as we have looked at, rainfall extremes across the world. We have looked at heat waves, cold snaps across the world. We have looked at precipitation extremes in India. And we have looked at coastal processes. So there is this process called coastal upwelling, which is very important for ecology, including marine ecology, and climate change seems to impact that. So we have looked at all of these with a combination of models and observations. And also agriculture. So recently, one of my PhD students, Shashank, has been working at the Oak Ridge Lab with some of our colleagues, Forrest Hoffman and Jitu Kumar, and they have been looking at how some of these methods could be useful in the context of agricultural production. And we have recently started to think about what all of these might mean for water and the built infrastructure across variety of applications. So water, food, energy, and infrastructures relevant for that, and what kind of information in general, whether it's about agriculture, whether it's about infrastructure or poverty, we can get from remote sensing and combination of remote sensing with models. Some of our work have looked at things like water energy nexus, where despite the significant amount of uncertainty, we can still get signals. And that's a very important message to convey in the context of climate adaptation and understanding of climate science. We do not want to minimize the uncertainty, but we want to do our analysis in a way that despite this uncertainty, we try to examine whether we can get signals. In many cases we can. There could be some cases where the signal is just not evident, and we have to be careful in acknowledging all of that. And we have also looked at urban heat waves. So, how urban heat waves impact public health risk. We did this work for the town of Brookline in conjunction with American Geophysical Union. One other area that we have looked at a lot recently is this whole area of lifeline infrastructure networks. So whether it's at regional scales, things like Indian Railways, US airports, or in city scales, London airports, Boston Rail, and Power. And a lot of this work was led by Professor Udit Bhatia at IIT Gandhinagar when he was a PhD student here, and he has been continuing his work. One other aspect that we have just barely touched upon, but needs to be looked at much more in the context of artificial intelligence agent-based systems, are social systems, human dimensions. So in terms of when we think about risk, we think about threat and human consequences and resources that can be brought to bear. This is in the context of risks related to water availability and water hazards. But when we think about social dynamics, processes, we need to go a little bit deeper. And there have been some work now in the context with agent-based models. We did some work in that area in a wholly different problem for the US Department of Defense, but some of these methods are being used now in the context of floods and climate change and agriculture and infrastructures. Again, validation remains a key issue there, so a lot of work needs to be done. We have done some work which are more practical, such as for climate ready Boston effort. And now some of my colleagues have been working in extending this work for Greater Boston. We have looked at variety of issues such as how coastal cities might be impacted. So risk-based assessment. Once something is impacted, such as New York City's mass transit is impacted, how it can be recovered. We have looked at not just engineering and scientific issues, which has been our focus, but also how things like financial incentives and regulatory principles, how they might interact to create a vicious cycle of climate maladaptation, which could be changed potentially with both better financial incentives and transformative science. Some of these have led us towards socially impactful, hopefully socially impactful startups and technologies in a similar vein as the as catastrophe modeling and hazard risk modeling did earlier. We have been looking at climate risk analysis. So RISQ risk is one of our lab's spinouts, which started off with one of our patents by Evan Kodra, who was my former PhD student and is now the CEO the CEO of risk. And then also looking at recovery of infrastructures, which is this patent built by, the main inventor is Professor Udit Bhatia. And we are still thinking of translating this into a commercial entity. So with that, thank you very much. No professor can, does any work without the students, postdocs, and so on. So here are some of them. It's a quick attempt to, I'll not go through all of them, but it's a quick attempt to at least make sure that all of us understand that, I'm just showing a whole bunch of work that was done by a lot of, very dedicated scientists who are now very well placed in industry, in academia, in startups, and in federal government, national labs, including NASA and Oak Ridge Lab, etc. With that, thank you very much. Happy to take questions.
Thank you, Dr. Arup. So it was very interesting talk indeed. For attendees, if you wish to ask any question, maybe you can type in your Q&A box. So there is a Q&A box at the bottom of the Zoom platform, and you can click on that and you can type in your questions there. And meanwhile, if panelists have any questions, they can ask directly here as an audio.
Hello, Arup. Hi, Arup. So it's a great talk. Thank you for this great talk. So I was wondering, what you were telling is that the cycles are getting lower and lower. The time for severe floods perhaps was previously 100 years, and now it is becoming 50 years, or this way things are actually going down. So how can, what type of modeling can we do to, because there can be two things which I feel. One is show this more and more to the policy makers and try to convince them that this is actually happening, and perhaps also build up a prediction model in a much better way so that we can deal with these things. I'm a bit lost. I just want to ask you that how, as scientists, we can deal with this situation or help in this situation. Yeah.
That's a very good question. So I think, one thing that, first of all, I'll tell you a little bit about, exactly your question, and then I'll go maybe a little bit philosophical into this. But in terms of exactly this question, how we answer it now is we have these, fairly complex Earth system models, and we look at their outputs, and they give some outputs at the scale of the globe, or in some cases, regional outputs. And then we look at observations, and then we see what happens, and we see, okay, 100-year events are becoming, in some parts of the world, or in an aggregate sense, 10, 20-year events. We see cases where, what used to be called 100-year events, they are happening. They have happened in the last 3 years and so on, right? So those kind of things we see. But in terms of policymakers where certain things gets a bit complicated sometimes is there is attribution and mitigation, and then there is adaptation. And even within mitigation, there are mitigation within across various scales. So sometimes we think that, to be able to stop consequential floods or floods that are potentially large but have significant consequences, the only thing that we need to look at is, reduce greenhouse gas emissions by X amount and floods will stop. That is not exactly how things work. So yes, it is important. It is important to be sustainable. It's important to have green energy. All of those things have tremendous value. But as a society, when we do risk benefit analysis, we also have to look at adaptation measures. We also have to look here in this part of the world or this part of the country, floods have been growing worse. Not just because of global climate change, that of course might be a contributing factor, but also because we have not been building our infrastructures right. We have not been able to keep pace with the degree of urbanization. The social inequality is very high. So let's say, for example, when floods happen in Mumbai, the people who are disproportionately impacted may be the people living in Dharavi. So maybe something could be done there. So if we take a little bit of a comprehensive view of what can be done, instead of this, single focus on, if we do this, then this happens. I mean, human mind works linearly. But these systems are very nonlinear, and there are many things, the geophysical system, the hydrology of the process, the urban system, land use, the infrastructures, which if they don't break, things don't happen, society, inequality, all of these things. And if as a planner, we can start to address these, lot of things can be done right there. So it's a multifaceted problem, and there could be solutions built that are multifaceted. Some have more costs on us as society, some less. So if we sort of understand this, maybe certain things will get better. And as a philosophical point, we have all, many times we have struggled, I'm sure you have, many of us, in terms, when we deal with this, people say, you should be an honest arbiter. You should not talk about policy, because the moment as a scientist you talk about policy, you are biased somehow. And there's this theory called honest broker. You have to be honest broker. And for a long time, I sort of partially bought into that. Maybe I shouldn't say anything. But then recently, with all the things going on, I've had this view that, let's say you live in a high rise and you live in the 48th floor, and there's a big tsunami coming. You know that not much will happen to you, at least initially, because you will survive. But there are people downstairs. Wouldn't you at least say that, guys, do something about it? So that honest broker view, I have been sort of rethinking a lot. So that's my philosophical answer to your question.
Thank you for this answer.
Okay, thank you, Dr. Arup. So actually, we have several questions coming from the attendees, but in interest of time, since we have like multiple talks coming after this. So in interest of time, we shall not be taking these questions, but we shall be forwarding you all these questions. Maybe if you find some free time, maybe you can answer some of these questions offline.
Of course, happy to answer them.
Yeah, thanks a lot. Thanks once again
for the invitation. Thank you so much.
Nice. Yeah, thank you. Yes, so now we have the second talk by Professor Srinivas Ravela, and the title for this talk is Stochastic Physics Designs of Informative Hybrid Learning Machines for Earth, Planet, Climate, and Life. So Professor Srinivas Ravela directs the Earth Signals and Systems group at MIT, where he is the principal research scientist in the Earth, Atmospheric and Planetary Sciences Department. His general research interests are in nonlinear dynamics and stochastic processes, with particular interest in information and inference. Dr. Ravela's research group conducts research in animal biometrics for conservation, cooperative autonomous observations of the Earth using unmanned aircraft, dynamic data-driven modeling for estimating risk from natural hazards in changing climate, fluid and seismic imaging, and exoplanet detection. So Dr. Ravela's group conducts methodological research in inference, information learning for stochastic system dynamics and optimization. Dr. Ravela is the winner of the 2016 MIT Infinite Kilometer Award for Exceptional Research and Mentorship. He is the co-founder of Wind Risk Tech LLC. He is also the head of the research and development at Galaxy AI, where vision and learning technologies are being developed for intelligent damage detection. Dr. Ravela studied stochastic systems as a postdoc and computer vision, robotics learning, information retrieval as a graduate student, earning a doctorate in computer science in 2022. 2002. So Dr. Ravela is present online, but we shall be playing his video, which is his research talk, and after that maybe we can have a direct Q&A with him. I hope the screen is visible. Can one of you please confirm?
Yes.
Yes. Okay.
Hello, my name is Sai Ravella, and this work is jointly with Margaret Troutner and Gabriel Margolis, both of who will talk at different parts in this presentation. My talk is titled Informative Neural Ensemble Kalman Learning, and it describes the application of stochastic systems theory to deep learning. The major point I want to communicate is that while many people are applying learning to systems problems, we will apply systems thinking to learning. A stochastic perspective of learning systems enables us to maximize information gain, to optimize the dynamics of learning. This is important to many problems, including stable hybrid dynamical systems and learning equations from data. The structure of my talk is as follows. First, I will provide some motivating predictive applications from our group that draw upon connections to autonomy, learning, vision, and the earth sciences. I will then summarize the systems paradigm that underpins the applications and the systems dynamics and optimization loop that is entailed for improving predictive skill and efficacy. I will then use this as a basis to motivate the study of stochastic learning systems dynamics and summarize this with a quick description of an ensemble, which is not the same as ensemble learning, approach to deep learning. This uncertainty-aware, adjoint-free approach helps quantify and maximize information gain, which we do for variable selection problems as a fast alternative to other sparsity promoting techniques, notably L1. Finally, we will apply this framework to an exciting holy grailish type of problem to learn the dynamics from data. Our group, the Earth Signals and Systems Group, is a systems science group embedded within the applied sciences. It is an interdisciplinary group drawing from the applied math, aeroastro, mech-E, CS physics, earth sciences, and other departments. The first project I'd like to highlight is work we did in developing cooperative autonomous observing systems. Such systems are of great interest in the ocean and atmosphere, but the challenge is to observe the atmosphere as sparingly as possible while maximizing information gain. And by sparingly, we mean sparsely. This is done in a closed loop, including model prediction, uncertainty quantification, adaptive observation, and back to model prediction. We are the earliest group deploying this approach to observing coherent structures like plumes and clouds. A second project involves the use of image recognition for individual animal identification with application to conservation. We have, I believe, one of the earliest, longest running, and largest biometric systems. A characteristic of our approach is a closed loop that uses human relevance judgments to improve recall, and we maximize information gain to obtain the best judgments. Of course, there are industrial applications of such fine-grained recognition that we are also pursuing. A third project involves quantifying the risk from extreme events in the atmosphere in a changing climate, and particularly we mean cyclones and the other risk that it entails. This is a difficult problem because climate models, such as those found in the IPCC, cannot resolve cyclones. The grid sizes are too big. So we develop a technique that uses physics and statistics to downscale the coarse climate to dynamically produce cyclones. These have been observed to match the historical record, without, of course, using the historical record itself for the modeling. This approach allows us to also quantify rainfall and flood risk. A key challenge is uncertainty quantification, where we use surrogate models, that is, ones that were learned for solving the backward Kolmogorov equations with active sampling, and again, this maximizes information gain. Another key challenge is decision support, where reinforcement learning and stochastic dynamic programming problems are of interest. And here again, maximizing information gain is key to targeting brackets of risk. That brings me to the last but not least area of interest, and that one that is the focus of this talk. In this area, we are interested in augmenting known governing dynamical equations with data-driven ones. creating neural dynamical systems, that is hybrid systems, whose structure is optimized with data. Again, we'll use an approach to maximize information gain to optimize the learning of such systems. The applications that I have just described can be methodologically framed in a standard systems paradigm. The word systems, of course, is being used a little bit loosely to include a broad number of areas such as estimation, control, planning, decision theory, etc. This paradigm consists of a dynamical system of some sort, usually a discrete dynamical system, and the model F as shown can be specified, or in our case, as we will do in this talk, learned in some fashion. The states are denoted X, controls or external inputs or forces are denoted U, and the model parameters are alpha. We have also an observation equation H and a set of goals G. The standard systems problems pertain to inference. These include a filter, a fixed point at initial time, a smoother, parameter estimation, and the controller. These are standard problems I want to emphasize, though the probabilistic way in which we have written this as an inference problem is a bit non-standard. Methodologically, in science and engineering, for example, F might be a fluid dynamical model with a million grid points. The equations may be highly nonlinear, even chaotic, and the observations may be sparse. We don't observe the Earth everywhere we possibly can't, and they may be noisy. The distribution associated with the state, the probability distribution associated with the unknown state variable, could become highly non-Gaussian. So solving these inference problems is quite difficult, especially if they must be done in real time. But we have to solve these problems, whether it is to figure out how to build an observatory, whether it is to figure out how to downscale, or whether it is to figure out how to numerical weather prediction. There is a sort of systems paradigm that underpins some of the problems that I have talked about in the previous slide. One way to idealize the solutions to the problem that we just presented in the previous slide is shown in this figure. And I just want to point out that it is common, this approach I'm just going to describe is common to numerous problems in engineering and sciences. I urge you to have a look at the handbook cited on this slide for those applications. Okay, so anyway, the loop begins with, in our case, a theory on the left-hand side. These could be governing equations that were derived from Navier-Stokes, for example, and then follows the blue paths. Numerical modeling is often used to produce high-fidelity models, which must then be reduced for real-time use, and in many cases, just to even make the simulation tractable. The result of this is that predictions have uncertainties. The standard approach to deal with this problem is prediction and correction. Many of you know this as the Kalman filter, or you might have used the particle filter, and the numerous variants in between. This involves using the data and predictions to recursively estimate the model parameters and states, or the reduced model variables, even the reduced model basis. In this standard loop, learning is increasingly of interest, particularly because model reduction leaves out detail that the data still has, and uncertainty quantification remains difficult for high-dimensional problems. In the learning systems augmentation too, theory may be used, for example, to synthesize the structure of the learning machine, for example, the neural structure, and loss may incorporate dynamical constraints. Unfortunately, the coupling between the physically based and data-driven aspects is anything but simple. To tackle the problem, we will turn to a different idea. In recent years, a kind of active paradigm has emerged in systems using information theoretic foundations. By contrast, the classical paradigm contains a closed loop, tracing the black arrows in the figure shown. It passes through model prediction, uncertainty quantification, and information fusion to combine data and models. Informative approaches augment the dotted lines with an additional feedback path shown in green that maximizes information gain for a variety of purposes, such as observing sparingly but strategically, selecting key input data, selecting key model parameters or states or control inputs, or optimizing the structure of the model itself to prioritize the fusion or update. As we have suggested, many applications have shown that doing so leads to efficacy, especially problems that are nonlinear, high-dimensional, non-Gaussian stochastic processes. For hybrid systems involving data and physics, this is particularly valuable as it allows learning by the data-driven part and estimation by the model-driven part to jointly and stably coexist, and both these processes can be jointly the same paradigm. Of course, I want to point out that the use of information gain for variable selection is not new and has been made common by approaches such as informative planning, informative sensing, and informative estimation. These are part and parcel of the same paradigm. But what is even more remarkable is how little the informative paradigm has been developed in learning itself. After all, the learning process is high dimensional, nonlinear, and leads to non-Gaussian uncertainties, and it can be thought of as a stochastic process. So there are several ideas within machine learning itself, including active learning, relevance learning, model selection, structured learning, among others. The informative approach unifies these paradigms. At the same time, the proposed informative learning approach that we are going to present has, to the best of our knowledge, not been shown before, and as we shall see, appears to offer some benefits over sparse optimization paradigms. And we'll see the connection between the two, then the sparse optimization paradigms that are currently in vogue. So to treat the ML audience here, we apply the informative approach to optimize the dynamics of learning itself and show that this makes the learning process more efficacious. To demonstrate this, in the remainder of the talk, we will focus first on the dynamics of learning, then derive the informative learning approach, and then apply it to a particular problem, which is to learn the dynamics from data. As an example of what types of benefit we derive, consider the example shown in this slide where we are interested in a hybrid system that is part physical, part data-driven. The idea is that we want one dynamical system, let's call it FL, which is, let's say, low resolution, to learn details it cannot normally represent from a high resolution model FH. This is also studied as a parameterization problem. So once the machine FNN is trained from perhaps simulations of a physics-based FL and a physics-based FH, a high-resolution model, training a low-resolution model, we may imagine that we'd add in the FNN component and somehow thus have a functioning hybrid system that mimics the behavior of the high-resolution system FH. Unfortunately, irrespective of the learning machine used, and this is an important point, if the training is offline, then things won't work because the injection by the learning component simply causes divergence. This is shown in the animation on the right, where the advecting low-resolution blue curve is to be augmented with detail that is in the dashed blue curve. The naive strategy of constructing the hybrid simply falls apart, as the brown curve and its axes show. When errors grow exponentially, such as for chaotic systems, this is an even bigger problem. So what can we do about it? If the estimation of FL and parameters of FNN were dynamic and data-driven, then we could estimate and learn jointly in a lagged manner, which would solve the problem as the second animation with the machine ML1 shows where the first ML0 machine fails. This type of learning of neural dynamical system is feasible through informative learning that we've just described and is an application we are interested in. Another problem is to learn the dynamics from data. Let's be clear what we mean by this. There is some dynamical system that is producing data, and this data will be discrete in time. In other words, it's not a continuously available solution, but it's in discrete time, and it's probably noisy. And what we want to do is to learn the dynamics. In other words, we want to give out the equations. This is the holy grail. I mean, forget model reduction, forget parameterization. If you could stick a sensor out there and out pops the equations, that would be of joy to the dynamicist, to the system scientist, to the machine learning person. This is the perfect, you might want to say, problem to be working on. So we'd start with an ab initio model, scratch, nothing, x dot equals to 0. And through the informative approach presented here, we will arrive at the correct model. Of course, we'll try this on a simple problem first, and we'll arrive at that model faster than we might do otherwise. We will show that the informative paradigm adds the kick, provides the efficacy. And this problem will be the main subject of this talk, in contrast to the stable hybrid problem, which for time limitations, we might not be able to go into, but I am giving another talk at AMS, which will be the focus of that subject. But I invite the viewers to discuss both of these applications with us. For either problems, we want to and will investigate learning as a dynamical system. In other words, we will begin with a description of the dynamics of learning, which allows us to solve for these type of problems using the informative paradigm, and which we argue is efficacious. So with this, I hope the overall motivation and methodological lay of the land is set. And I will now turn to some details towards the development of the informative paradigm with application to learning dynamics from data. Our proposed methodology begins by considering the neural network, which we may normally write as a monolithic function as shown in equation 1. It consists of the input x0, the output xn, and parameters which represents perhaps weights and biases. We may also open this up to reveal a multi-stage process proceeding from layer to layer. So here in equation 2 and 3, we express classical feed-forward and recurrent networks for an end-stage process. We include the training output as a noisy observation at the terminal stage to model label as well as network imprecision. Feedback and feed-forward components are presented in the standard system sense using the term U and require additional equations for closure. For example, in the top figure, we show a multi-stage process model of the neural network with feed-forward and recurrent components. Another class of system that is more familiar to us is the dynamical system. Here shown in equations 4 and 5 are an autonomous system with constant but unknown parameters, no process noise, and observations with errors. The interpretation is classical, and we consider such representations later in the talk to model neural dynamical systems, which are systems that are described in part as neural networks. Thus, we commence with a system's definition of the network as a multi-stage process, and that of a neural dynamical system, where the process is at least in part a neural network. The system's representation immediately provides the basis for learning as a parameter estimation problem as shown in equation 6. The performance index minimizes the error norm between the network prediction and training output, respectively xn and yn, and it's adjoined with multi-stage dynamics. You should recognize this immediately as a two-point boundary value problem that's common to a vast number of inverse problems. The normal equations in 7 through 11 reveal the familiar forward-backward algorithm.
also known as the adjoint method, 4D-var, among many other names. But this is exactly what backpropagation is, though ironically, the original Rumelhart et al. Paper does not mention this result, found in Bryson and Ho's optimal control book much, much earlier. From the forward-backward pass, we obtain a parameter gradient, and many methods from gradient descent to semi-Newton methods could be applied, and this is then just a classical optimization problem. So what's the big deal about writing equations this way, you might ask? Well, three things. First, there's no mystery behind backprop. We know it. We know these equations. But we also know many other things, such as finite time Lyapunov exponents, which we could now bring to bear, say, on the aerodynamics of the adjoint equation and beyond. There are many other problems where it could be applied, perhaps in the design of better networks. So this is just an ideation or an idea we're putting out there with no support in this paper. But this is just to say that there are many things that can emerge by bringing learning into the standard frame. Furthermore, and this is what we do here, if we consider that the gradient is calculated for a mini batch, then obviously gradient descent becomes a stochastic process. Well, this could then be expressed as an Ito equation, whose Fokker-Planck equation describes the evolution of the distribution of weights alpha in time as the network perhaps converges, implying that learning has occurred. We present the details of the stochastic formulation in the archive paper cited at the bottom of this slide, but we omit further discussion here, except just to note that the Fokker-Planck equation immediately leads to the ensemble approach, but this is also well known. This is perfect, however, because the ensemble approach provides a uniform basis for informative learning, which is what we explore in this paper.
Let's trace the stochastic process argument one more time. Let's start by looking at the gradient descent shown on the top left. We can, to be sure, also derive what we're about to discuss for other iterative approaches, but we just do it for gradient descent here. So on the top left, we have gradient descent, which we have written for a mini batch. And this is written as grad j bar. And once we get this, we can write grad j bar as a perturbation over the whole batch gradient average. So the whole batch average is mu, the perturbation is w, and this depends on the weights or parameters alpha that are changing over iterations. Now, if we model w as a stochastic process, and because it's a perturbation, it's zero mean, and it has an expansion, and you can write a KL sort of expansion for it. And all we've done here is use a Gauss-Markov process. So from this Gauss-Markov process, we immediately can substitute back to derive an update equation in the continuous limit, d alpha t, for the continuous evolution of weights, known as the Ito equation. This equation may also be written in Strantanovich form, but this is easier this way. But notice that this is not the Langevin equation. Don't confuse this with that type of learning. What is happening here is we've written an Ito equation with a drift and a diffusion process. And this has an associated Fokker-Planck equation that allows us to describe the evolution of the probability of the weights, or P alpha. So dP dt describes the partial differential equation that tells us how the distribution of weights evolve. And so if we have a learning system that is undergoing gradient descent, the gradient descent, because of the use of mini batches, turns into a stochastic process, which we have characterized by its Ito equation, which has an associated Fokker-Planck equation that tells us how the uncertainty evolves. From a stochastic systems perspective, this is really just standard. I've just described one part of a class to you, but from an ML perspective, I think this opens doors. I know there are people who are looking at this, particularly Tishpi's group et al. And there are people who've looked at this, but I think this perspective is still not well developed. The beauty of this approach is, for example, that it allows us to think of stochastic optimal control to optimize learning. One simple idea could be to optimize the mini batch size by controlling the dispersion of P alpha. over iterations. So although the notation here might seem complex, from a dynamical systems perspective, there's really nothing new. But from a machine learning perspective, it could be quite interesting. So what would knowing the equation for P alpha give us? I mean, what does the Fokker-Planck give us? A lot. A lot. For example, the mutual information between the data D and the parameter random variable A can be used to characterize the efficiency of information transfer. Did you just build a bogus machine, or is your neural network really good at transferring information from the data to its internal weights? This can be quantified and perhaps can be maximized, right? The mutual information between data and prediction errors can be used for input selection. Similarly, we can perform parameter selection and structure selection, that is how to reshape the neural network by adding or deleting nodes. All this can be done. These optimizations will require work, no doubt, but nevertheless, the framework is now there. We have a very clean stochastic process model. We have a very clean Fokker-Planck model connecting with a lot of physics, and we have this notion of information gain, I, that we can optimize. And as we shall see, the use of information gain for selection is also a sparsity promoting optimization paradigm, but it is based on entropy, which, as we've shown, is a much sharper approximation to L0, which is the true sparsity problem, than L1. It is also fully aware of uncertainty, which L1 is really not. So this leads to a greedy sparse optimization approach that is much faster than L1, offers competitive, if not better, solutions. All this is to come, but for now, we can imagine these benefits here. Okay, so all this theory sounds fantastic. And the question is, well, how are we going to use it? Most deep learning happens without uncertainty quantification at all. Every time you go in there and do backprop, you don't get anything back. No pun intended. Even when Bayesian approaches are used, including Bayesian optimization or say variational Bayes, it's not really tractable in such high dimensions as most deep networks live in. And here we're talking of Fokker-Planck equations and characterizing mutual information with them, which appears even more ridiculously impractical. Luckily, we have a tractable approach that is also known as the ensemble approach. This simply consists of sampling an ensemble of parameters, solving the forward equations, in this case a neural network, then evaluating the prediction errors and statistically calculating the adjoint for a parameter update. Now, the statistical calculation of the adjoint is through samples, and remember how to take a gradient by sampling. And this idea has been applied to filtering and smoothing problems, where it is known as the ensemble Kalman filter and smoother. For the filter, here we show an example of estimating the state of a chaotic dynamical system, just to give you a sense of the cadence. Between observation, the error grows. Then when the observation hits, it shrinks. The important point here is that there is no linearization of the forward model F between this prediction correction cycles. This is not the extended Kalman filter. This is not for a linear problem. The model F is fully nonlinear. Yet we are not stuck in it, and we are not stuck in a terrible sampling regime like the particle filter. There is propagation and update, which can be very compact. The update is just sort of like a message in a graphical model. I mean, please see the reference for more details of tractable smoothers and other ideas. So what does this mean for learning? Sample the weights, make the prediction, update the weights in parallel. In parallel, there is no backprop, gone. We have uncertainties of weights available. We can quantify and maximize information gain. And so this is the ensemble Kalman learner, a simple yet highly practical and effective approach to learning. Much simpler than variational Bayes or Bayesian optimization, but convergent to backprop. Extensions of this idea to non-Gaussian problems with mixtures and kernels have also been done, and the citations are here. So next we'll hear from Gabriel, who implemented this for deep learning.
The ensemble approach uses perturbations of the parameters with many batches of training data to arrive at an update rule similar to the ensemble Kalman filter. Using the definitions of variables shown in this slide, the update to the parameter ensemble matrix A sub I at iteration I using matrix M is weakly nonlinear. We note here that other loss functions, including, for example, mutual information or optimal transport, are also admissible in the ensemble framework, as are other distributions controlling the parameters or targets, such as mixtures and kernels. We've shown this form here for the simple reason that it is easy to understand and offers a direct alternative to backprop. We also note that the ensemble approach to learning is receiving some attention in the literature. However, the results, as we also saw initially, were not that great until we started applying an adaptive version of the filter. In our version, the tolerance with which the label or target is matched is adapted over iterations. As we shall further see, coupling with information gain truly turns this approach into a valuable method. The ensemble learner defined in equation 14 updates parameters in parallel. There is no backpropagation, so this removes the sequential back and forth. Thus, this approach is also in stark contrast to variational Bayes, a popular but relatively quite expensive form of Bayesian learning. The ensemble Kalman learner also quantifies uncertainty. As a result, the joint distributions of key variable pairs, such as errors in parameters, errors in training data, errors and new structural terms, become available. These distributions can be used to quantify information gain and optimize it for a variety of objectives, as we shall use for learning dynamics from data. A first example of the application of the ensemble Kalman learner is to the Boston housing dataset, which is a relatively small dataset. We refer you to the paper for the network structure and dataset details. The ensemble learner converges at a faster rate and more smoothly while estimating the parameter uncertainties. Please note that in the right graph, the initial parameter uncertainties are small, but this is the case of a high bias but low variance. The total error is still large. As the training proceeds, the test errors indicate a lowering of the test error as well as variance. The costs are competitive, if not better than, backpropagation. A second example of the application of the ensemble Kalman learner is to the MNIST housing dataset. We refer you to the paper for the network structure and dataset details. The ensemble learner converges competitively and more smoothly while estimating the parameter uncertainties. Please note that in the right graph, the initial parameter uncertainties are small, but this is the case of a high bias with low variance. The total error is still large. As the training proceeds, the test error indicates a lowering of the test error as well as variance. Again, the computational costs are competitive, if not better than, backpropagation, while quantifying uncertainty. Kindly refer to the paper for details, including access to the implemented examples.
The ensemble learner allows us to maximize information gain for a variety of objectives. We maximize for variable selection in this paper, which is an L0 problem. The objectives may include parameter selection, such as in a resource-constrained setting, input selection, for example, to turn big data into smart data so we're not evaluating all the data, structure selection to optimize the structure of the model, among many other possibilities. So suppose we had two random vectors represented by their ensemble matrices. Here we're going to use A for parameters and E for the network prediction errors. We can then quantify pairwise mutual information between the random vector components, which we do here by assuming Gaussian distributions. The pairwise mutual information psi ij between vector elements ai and ej can be sorted. Again, to information selection criteria that's quite popular in machine learning, especially the old style machine learning, penalizing the number of terms selected against the expected increase in information, we arrive at a greedy solution to the L0 problem, which produces a subset of A terms, or if desired, the AE pairings that we are going to select for subsequent use. The greedy L0 problem approximates an NP-complete problem, but it can outperform solutions to the L1 approximation like lasso, as many people have shown. In addition, the greedy solution can select terms ab initio, which is better than, say, Monte Carlo, and better than many versions of, say, MCMC. It is also better than variable elimination from, say, a large initial set, for example, using L1, where elimination occurs when the weights of the parameters are driven down to very small values over iterations. So this approach involves no iterations and is both memory and time efficient. It's a simple greedy solution to an approximation to the L0 problem. And the use of information gain allows for that. It can in fact serve as the maximizing information gain part to the ensemble learner so that in a coupled manner, they can solve problems. And this can be done with or without lasso-like constraints. This, of course, is at the heart of DDDAS and leads to the new informative learning paradigm. We now turn to the application of the informative learning paradigm, which couples the ensemble learner with maximization of information gain. We pick the structural learning problem, which is to estimate the structure of the neural network and its parameters. In particular, we are interested in neural dynamical systems, which, as we've described, are systems that are in part described by neural networks. What we want to do is to learn the structure of f of x in the dynamical system x dot equals f of x when we only have noisy discrete time series data, x1, x2, and so on. Unfortunately, this is a very difficult problem. It is difficult to assess structural optimality without knowing ground truth, but if the ground truth were equations, it is still very difficult to interpret the neural network in how it matches those equations. Of course, the use of learning brings generalization problems with it, and we can say very little about extrapolation. So it's not trivial, other than in some simple local sense, what structure was learned for the neurodynamical system. And to overcome these issues, we restrict the problem to a special but broad class, nonlinear dynamical systems with polynomial dynamics. Such systems are increasingly of interest for several reasons. First, in continuous or discrete forms, they have exact neural networks. This means that learning the neural representation correctly reveals the dynamical equations, or in other words, we would have learned the equations from data. There is much interest in this version of the problem, that is, how do we learn the dynamics from data? However, to be sure, we are interested in the general problem of structural learning using informative neural ensemble common learning, for which this use case is great validation.
As an example, consider the chaotic Lorenz 63 system of equations, which contain a quadratic nonlinearity, as shown in the left figure. The discretized version of these equations, say using a Runge-Kutta fourth-order method, has an exact neural network, as shown in the top panel in the middle. In other work, it has been shown that compact recurrent neural networks exactly implement both Runge-Kutta and Adams-Bashforth-Moulton schemes. In fact, they are exact for a large class of explicit and semi-implicit methods. Embedded within the RNN is a polynet, which is the exact neural network corresponding to the polynomial equations, as shown in the bottom panel in the middle. This representation contrasts with other work in the sense that our neural representation of polynomials is exact. These networks are constructed trivially from the equations themselves, and thus we have discrete time neural dynamical systems. As the right figure shows, the neural and numerical simulations are identical, but for floating point error at 10 to the negative 16, which, as the equations say, will also grow chaotically. So if you want a neural network for the Lorenz system, just compile this and run it on a tensor core. Thus, we can perform structure learning problems on a numerically simulated version of the Lorenz equations, using the simulated data to train the polynet scheme we have just described. From the network recovered, we read out the equations to reveal what dynamics we learned. We have to be clear that the training data will be both noisy and discrete in time snapshots, although in our experiments the noise is quite small. One way to solve the structure learning problem for the Lorenz system is to start with many polynomial terms, shown here in the orange panel by variable x. Then we can use ensemble common learning in the normal manner described earlier for parameter estimation. We perturb the coefficients associated with these terms, which are the weights. We use the ensemble common equations to update iteratively from a mini batch of data, which are short perturbed simulations from an initial condition. In the way we do it, it is not even guaranteed that the ensemble perturbations are on the attractor. Nevertheless, we stop parameter estimation when there is no further improvement to the error or error variance. Along the way, whenever a parameter's coefficient is close to 0, we remove it. This way, we recover the correct Lorenz equations, but after many iterations. This experiment is also a little too good to be true, in the sense that all the correct terms are in our original set X, and we haven't confounded it with too many. Still, it takes too long. We apply the informative ensemble common learner in the second approach. This one is difficult relatively in two ways. First, we start ab initio, that is, x dot is 0. We know nothing. Second, there are no particular bounds on terms that could be selected. We then make predictions, which is persistence for a parameter ensemble, and then maximize information gain as previously described. This gives us terms, and we then proceed with ensemble common learning iterations, stopping when variance cannot be reduced, eliminating terms with close to 0 coefficients, then repeating. The correct equations are recovered quickly and much faster and in only 1 or 2 term selections. Thus, the coupled information learning and parameter estimation process, a DDDAS principle, efficaciously recovers the dynamics from data. This chart shows the terms on the x-axis and the ensemble common learning updates on the y-axis. Terms selected at any point during the algorithm are in blue and green, the blue ones being terms rejected by greedy information gain maximization. The final surviving terms, which are in green, are the correct terms. These two charts show convergence. On the left is the convergence of coefficients with 10 to negative 4%, and on the right, the variance of the surviving terms converge. Please note that between variable selection, indicated by the dashed line, the parameter variances of the new terms are rescaled when they are first added. In conclusion, we think the days of backpropagation may be numbered. This is especially true if we want to leverage parallelism and quantify uncertainty. We also believe that informative learning, a principle espoused by DDAS, is here to stay, and insofar as learning or estimation, or for that matter control is concerned, the added benefit of controlling the instrumentation, which we here took to be maximizing information gained by variable selection, is advantageous. Because learning is a stochastic process, the application of ensemble methods is quite fortuitous in the presence of other difficult Bayesian schemes. No doubt, particle methods can be applied, which we'll do in future work. On the other hand, in the problem of structure learning, we can produce exact networks for certain non-trivial classes of dynamical systems. Thus, we are able to show the correctness of informative learning, with uncertainties quantified. And we do this without resorting to classical L1 sparsity paradigm, but to use informative learning, a DDS principle, to provide an alternative approach to that same sparsity. From another perspective, our approach, while normal from a stochastic processes perspective, clarifies certain details about deep learning and provides it with a consistent, common approach. Insofar as learning itself is concerned, informative ensemble common learning is new. There are many immediate extensions, both non-Gaussian information gain and parameter estimation, the development of network tuning using finite time Lyapunov exponents, and the stochastic control of learning are all of interest.
So thank you, Dr. Sai. Dr. Sai, are we audible?
Yes, I'm here.
Yeah. Okay, that's very good. Okay, so like we have one question which has come from the attendees, that how would this idea on parallel optimization work on large scale systems?
Well, it will certainly work much better than iterative methods on large scale systems because it's parallel. Recall that the update equation that you have is you get an update matrix that can be quite compact, and you can update all the layer weights in parallel. You don't sequentially propagate information back, so you do it in parallel. So in fact, if you have a larger network, the advantages would be larger. If you can provide the parallelism. If you don't have the parallelism, everything runs on a single processor. Well, nobody here wants to run anything on a single processor anymore. But if we assume we have these updates, perhaps even a distributed sort of GPU architecture where it is possible to pass a message, which is the update matrix, similar to a Kalman gain. If we pass that message across, then the updates will happen in parallel. The key problem is the iteration that's happening through the layers that slows things down. But we can, by trading the forward-backward iteration for the ensemble, do two things. First, parallelize. Second, quantify uncertainty. both of which are missing with backprop. And of course, if you assume that in the limit, the the stochastic approximation to the gradient holds, then this converges to the backprop. But that's not an argument we are making. Okay, so I hope that answers the question.
Yes, thanks a lot. Thanks a lot, Dr. Sai. Yeah, so anyone from the panelists wishes to ask any question?
I think Arup has a question.
Yeah, please go ahead.
Yeah, hello, if I can. Thank you very much, Mayank. So Sai, this was very interesting. We can get into details of the mathematical equations. I mean, eventually, this may not be the best venue when we get time, Sai, beyond writing proposals. But I had one question for you, which may be more relatable, I mean, overall. So in Earth systems modeling, we talk about data assimilation, variational data assimilation, as a matter of routine these days. You talked about 4D-VAR, for example. Data assimilation have been compared with recurrent neural networks, some aspects of it with back propagation, et cetera, and you referred to that in your talk. And there are some comparisons in that context of Earth system modeling, what they do with, in the context of data assimilation with Bayesian networks. And then from Bayesian networks, that makes me think of Judea Pearl, his causality, do calculus, etc. My question is the following. Given this kind of similarity or this kind of crossover between these concepts, why is it that when we think about these deep versions of recurrent neural networks, whether it's LSTMs, whether it's something else, why is it so hard to assign uncertainties? I mean, of course, I know about the approaches, I mean, some of the Bayesian deep learning approaches, but it's still very hard. On the other hand, if we think about data assimilation, it comes as matter of routine. Conversely, it is, when we think about Bayesian networks, these kind of things, that's sort of, in a sense, forms the basis of Judea Pearl and his, his causality and so on. But then when we think about climate attribution, the way it's done, somehow they fail to take advantage of any of those, I would say serious, if I can be so bold as to use the term, some serious developments in causality. So you're bringing this, some sort of analogy here, but why are the fields not evolving to take advantage of the other, where climate can do causality a bit better and deep learning can do uncertainty a bit better? Sai.
So I think there were at least 5 questions in your statement, but let me see if I can tease them a little bit.
I thought there were 11.
Okay, very good. So but we'll expand on that set. So let me start by simply saying that the field of data assimilation itself, this is being broadcast live, it's being recorded, there's 200 witnesses. So the field of data assimilation itself is just properly a branch of estimation theory. There is really nothing much else to say about that. There's nuances about how it's implemented. There's details about what types of inverse problems are solved, but it is essentially a branch of estimation, state and parameter estimation, largely. There are other things involved. And there's a well-developed history of this. I urge everybody to look up Bryson and Ho's Applied Optimal Control book from 1967. Its first chapter describes essentially backprop, or the forward-backward algorithm. He goes on to derive the Kalman filter, the Rock-Tung's tribal smoother. He talks about stochastic dynamic programming. He talks about differential games. It's all there. If you want to talk about the precursor to learning, it's there. But this is the same precursor to data assimilation also. In other words, learning and data assimilation just happen to be different sub-branches of specialization of some kind that have the same common root. In fact, if you go to reinforcement learning or learning for control, you see these similarities much, much more closely. So why is data assimilation doing something someone is not? I don't know. If you look at Hinton's original paper, Rumelhart et al. Paper on backprop, the Nature paper, if you look at it, it beautifully describes what's happening, but it doesn't mention adjoint dynamics. But that is what is all that is happening is an inverse problem is being solved with adjoined with the dynamics of the neural network. And that was missing. So maybe it was maybe it came from a different pedagogy, but time has a way of unifying all these things. So that's what is maybe is happening right now. Now, the incorporation of uncertainty is obviously a big issue. If you go to data assimilation field itself, as you know, ECMWF still uses the variational technique. And the ensemble is a bit controversial. There are many practical issues one has to overcome to make them really work for very high dimensional problems. Because if you think about very high dimensional problems, the ensemble will always be reduced rank. So if you think about a covariance of an ensemble, it'll always be very low rank. So how many updates can you get with something that is low rank? In fact, I feel this problem goes away somewhat in the neural network because you could do it layer by layer where you can build up the rank, which you cannot do in a dynamical system. So that's the second aspect to how I would think about this. So uncertainty has emerged in data assimilation because it's important for the living. If you give a forecast that says, I am pretty confident about my estimate, you're probably going to lose your job faster than if you said, I am 10% confidence of precipitation within the next 5 days. This sort of communication of uncertainty is very normal. Think about what happens in neural networks. When was the last time somebody said that the training output, so input is X, output is Y, the training output is uncertain? It's not until very recently that we've started even talking about label noise. So there is a certain determinism, there is a certain perfection to this training data that simply reality doesn't reflect. And as that happens more and more, they will have to think about this. So how did they think about this? Well, obviously Bayesian learning was the way to do it, which is this big fat amalgamation of, or this, I'd say, force fit of Bayesian inference and deep learning. I say call it force fit because on the Bayesian side, you have beautiful theory, you have graphical models. Everything that I have described today could simply be expressed as update on a graphical model. And the neural network is a graph. You're just doing a model update on a graphical model where each node is probabilistically described. The forward-backward algorithm can be equivalently described by Baum-Welch algorithm, or perhaps even the Viterbi algorithm. And these are all well-known things from graphical model perspective. So, but graphical model, I think computer science has had this way of complicating its life by going into the most general probabilistic distribution, and now you're stuck with what to do with it, and all you can do is sample. And then you tend to solve difficult problems without seeing what may be simpler problems that could be much more tractable. And so when you think about Bayesian optimization, variational Bayes, all of these ideas that have been stuck with neural networks, you never abandoned the forward-backward iterations. It was, in fact, you added on top of it, and you made things even more complicated. People then jump into like all sorts of non-Gaussian ways of describing entropy. I think that when you scale these to very large problems, these type of things kind of disappear because there is a trade-off between obtaining first-order estimates of uncertainty, if at all, versus doing something that is rich in its representation of the uncertainty. I think that trade-off is missing in deep learning, I would say, and therefore they went a certain way, which is, I think, to complicate things. But people who do data assimilation don't have that luxury. They still have to give the error bar around the forecast, and they obtain the most practical, perhaps, methods. And this could impact, in fact, perversely, or in fact, I would say for the good, neural networks as they become deeper and deeper and they become really large, you're going to have a really huge problem. So that, now coming to causality, the inference problem we've talked about here has no causality because it's just inferring parameters. Whether we can take the data and build causal representations from them and use that as a basis for representing dynamical systems. Now you mentioned LSTM. Look at what's happening. It's a very complex, again, there's 200 witnesses. I'm live, but I'll say it. It's a very complicated way of representing memory. Are you kidding me? These pipes and plumbing with respect to things passing back and forth, it seems very complicated. Memory is automatically represented. If you write a continuous time dynamical system, x dot equals f of x, there are such memory systems throughout the physical universe. Pick any system that has a power law spectrum, it has memory. So you can easily think about representing memory through spectra by thinking about differential equations and their operators. So why did we not think about differential equations as neural networks. It didn't until the neural ODE paper showed up that such a thing even emerged. But the neural ODE paper is kind of, I would say, a joke, because all they did was change x dot equal f of x from f of x being something general to being a neural network. And the rest of the Hamilton-Jacobi-Bellman equations are identical to what's in Bryson and Ho's book in 1967. It's the same idea. So the bringing in the continuous time dynamics, where these dynamics are not perfectly known, and in the limit, when instead of discrete time samples, as that limit collapses to a continuous variable, we get a lot of leverage, because if I give you an ordinary differential equation of the kind x dot equals ax, its solution lives in e power a delta t. There's an exponential growth. Would you rather fit an e power a parameter or an a parameter? So in other words, there is a sense in which, as these continuous time equations come and we can march them forward and backward along the timeline, we might be able to do something better, slightly better than these discrete time memory systems like LSTM. The extrapolation comes naturally to x dot equals f of x. Apply Rangakuta on top and you can numerically do it. Much better. And interpolation comes much better too. If you have an LSTM, what do you do in the time in between? Easier for x dot equals f of x to do this. So you can think about rainfall being interpolated at very high time scales, fluid flows. Now we can talk about hybridynamical systems, like my talk says, where some part of the operator, differential operator, comes from the physics, some part is data driven, and there is a universal common machinery that is based on, you can pick your choice, graphical models, variational mechanisms, but there is a single common mechanism. The two things that we are doing differently are, rather than follow the deterministic optimization and then stick all sorts of constraints like L1 and so on, we just said, let's jump directly, if we can, to probability. And that probability not only gives us the variational solution tractably under certain regimes, but it also provides the sparsity basis for doing information selection that would otherwise have been very hard and has not typically been done. So I hope this lay of the land that I'm sort of almost repeating kind of communicates this. Now that we are here, maybe the continuous time neural dynamical systems can help address the causality question that we were talking about.
Dr. Sai, sorry to interrupt you. Actually, in interest of time, I have to stop you.
Okay, I stopped.
Sorry for that. Yeah, but thanks a lot for accepting our invitation and for this very interesting
Thank
talk.
you so much. I hope this was useful.
Yes, it was very useful and it was very interesting too. Thanks a lot. Thanks a lot.
Okay, thank you so much. Okay, bye now.
Bye, Dr. Sai. Yeah. So, our next speaker is Dr. Ankit Agarwal, and the title for his talk is AI and High Performance Data Mining: Illustrative Applications in Material Sciences. So, Dr. Ankit Agarwal is a research professor in the Department of Electrical and Computer Engineering at Northwestern University, USA. He specializes in interdisciplinary AI and big data analytics via high performance data mining based on a coherent integration of high performance computing and data mining to develop customized AI solutions for big data problems. His research has contributed to large-scale data-driven discoveries in various scientific and engineering disciplines, such as material sciences, healthcare, social media, and bioinformatics. So he has co-authored more than 150 peer-reviewed publications, co-developed and released 15 plus softwares, and delivered 4 keynote and 40 plus invited talks at major conferences, universities, and companies across the world. Been on program committee of 35 plus conferences, workshops, and served as a PI, co-PI on 15 plus sponsored projects funded by various US federal agencies like NSF, DOE, AFOSR, NIST, DARPA, DLA, as well as industry like Toyota Motor Corporation, Japan. So in particular, he is one of the very few computer scientists who are actively introducing AI and advanced data science techniques in the field of material science, and has successfully led several large-scale machine material informatic projects. So as an example, he is co-leading the AI group at Center of Hierarchical Materials Design, which is a 60 million NIS-sponsored Center of Excellence. He is also serving as the editor-in-chief of Computers, Material, and Continua. Over to you, Dr. Ankit.
All right. Can you see my screen okay?
Yes, it is visible. Yes.
All right. So thank you so much for this kind invitation, and hello and good morning to everybody in India. I hope everyone is staying safe and healthy
And I really wish we could have had this conference in person and met all of you in person, but I guess with the pandemic, this is the next best thing. So today I'll be talking about AI and high performance data mining. And we'll also look at some illustrative applications of the same in material science. These are my team members, collaborators, and the funding agencies that have supported my research. So let's begin. This is going to be the overview of this presentation. I'll start with some introduction paradigms of science and some basic terminology, AI, ML, DL, data mining. There are so many buzzwords. So we'll try to clear it up a little bit. And then most of the time I expect to spend on illustrative examples of AI and first AI and high performance data mining, and then deep materials informatics. And then in the end, if I have time, I'll try to give a demo of some of the tools that we have developed. All right. So this is actually my take on the theme of this conference, and I like it very much because it very succinctly captures how artificial intelligence actually enables and accelerates science, and then how science in turn can aid the development of better AI models by providing the right kind of data that AI models need, and challenges, the real world challenges uh, for which the AI techniques are developed. So when we talk about science, there are many aspects. Of course, there are different fields of science, but there are experiments and simulations, and all these provide rich data that can go back to the development of AI models, which in turn can again accelerate science, and this symbiotic relationship exists. So to understand about this a bit more, it's useful to look at the paradigms of science. So if you look at how science and technology has evolved over centuries, not just years or decades, we can very clearly identify these four paradigms of science. So in the very beginning, all science was purely empirical. Everything was based on observations. And today that is famous as the experimental branch of science. So you actually do experiments in the lab, and but of course it is very costly and time consuming, so you can't do all the experiments. So in the 17th century, when calculus was invented, we could take real world phenomena and then express them as mathematical equations or laws. So things like Newton's laws of motion and laws of thermodynamics, they are good examples of the second paradigm of model-based theoretical science in material science. Then over time, these equations became larger and more complex. So it was not possible to solve them analytically. So in the 50s, when computers were invented, we could now solve these equations on computers and then supercomputers. So that led to the third paradigm of computational science or simulation-based science. And good examples of that in the materials domain are density functional theory, molecular dynamics, finite element simulations, and so on. Over the last couple of decades, just the sheer volume, velocity, variety of the data that is being generated by these first three paradigms has far outstripped our capacity to make sense of it. So that's where this fourth paradigm of big data-driven science comes into the picture, where the data itself is a resource in addition to all the computation that we have. Just the historical data can be used to identify patterns and drive discoveries and get actionable insights. So needless to say, this is nothing short of finding a needle in a haystack. It's a very challenging problem. And I like this example in particular because not only this signifies the difficulty in finding the right needle, but also the ease or the risk of easily finding the wrong needle. In other words, if we just take some technique and take some data and put them together, the AI techniques are domain agnostic. So they don't really know where the data is coming from, what it stands for, what are the assumptions, and so on. So it will churn out some numbers. And if you're not careful, if you blindly apply them, we can very easily fall into the trap of these wrong needles. So it's very important to have the right kind of domain expertise, the right kind of AI expertise in order to apply these things coherently. So let's talk about these buzzwords. What is it all about? So what is exactly AI? AI is nothing but the ability of machines to perform tasks that normally require human intelligence. So it's a very broad field, and there are many subfields within that, like robotics and expert system, machine learning, and so on. There is an interesting classification of AI in terms of weak AI, strong AI, and super AI. And interestingly, all the AI that we know as of now, even the state-of-the-art example of self-driving cars, that is also an example of weak AI. And that means that you can build an AI model which can do a particular task very nicely, as well as humans, or even better than humans, like, for example, playing chess, but it cannot do anything else. And strong AI is when you can actually do a variety of things just like a human does. And super AI is beyond that. So all the sci-fi movies that you see, that's all based on that. But that's not happening anytime soon. So AI is not taking over the world anytime soon. Then within AI is this machine learning, which is focused on the ability of computers to learn without being explicitly programmed. And as you can see, these concepts date back, to 1950s. So this AI ML has been around for a long time, but they always have been hungry for big data and big compute. And that's where deep learning comes in, which is nothing but rediscovery of neural networks fueled by the availability of big data and big compute. So now that we have lots and lots of data and lots and lots of compute power, we could actually make these networks deeper and fulfill their promise of being universal approximators. And I'm sure you've heard of a lot of deep learning success stories, from game playing to computer vision, natural language processing, autonomous driving, and so on. So practically deep learning is driving a lot of modern technology today. But like any other technique, deep learning has its share of advantages and challenges. So we already talked about how deep learning requires big data and big compute. Architecture search and interpretability are also other challenges, because these are basically open problems, because there is no optimal way to find the best possible architecture for a given problem at hand. Although there are some guidelines, depending on the kind of data you have, you can have what kind of layers to use, what kind of connections, and so on. But there is no way to get an optimal architecture, just like that. And similarly, neural networks are at best limited in their interpretability compared to traditional data mining algorithms like decision trees and so on. They are more readily interpretable. And deep learning models are generally considered black box or gray box models. Although there are some techniques like saliency maps and activation visualizations that can give you some idea, but it's more challenging. But typically the advantages of deep learning, which I list here, often outweigh the challenges. So the biggest advantage of deep learning is that it is feature engineering free. So you can actually work on raw data. You can give lots and lots of raw data, and if you have enough of it, deep learning can figure out the features itself, rather than, for a long time in machine learning, we have had to handcraft features for machine learning. But if you have enough raw data, it can figure out the features itself, and then features of features, and then features of features of features, and that way it can work on raw data. Then it also gives more accurate models, as you can see here. For low amount of training data, deep learning models are not so accurate, but there is a crossover point after which the deep learning models are more accurate, and they don't saturate that quickly. And of course, this crossover point depends on the problem and the data that you have at hand. And we have been able to identify this for some of the problems that I'll show later in this talk. And then these models are very fast. So it requires big compute to train the model. But once we have trained a good deep learning model, they are very fast to churn out predictions in a matter of milliseconds or microseconds, or even less. And it's trivially parallelizable. So you can solve inverse problems very fast. And we'll get to that. Deep learning comes in different flavors for different tasks. So this is the most traditional neural network, fully connected network. So if you have numerical data, you have this input layer, output layer, and a bunch of hidden layers. And you pass the training data through this and get the error, and then back propagate the gradient of the error with respect to the weights of these edges to update the weights. And you train the network in this way. And when properly trained, it can then take new data as input and give you the predictions. If you have image data, convolutional neural networks are very popular and have shown remarkable success. It also gives a nice property of spatial invariance and avoiding an explosion in the growth of in the number of parameters. So CNNs are very powerful for image data. Anything to do with the sequence, like language modeling or weather prediction and time series. We have RNNs and their variants like LSTMs and recently transformers and so on. And then these generative adversarial networks are a special class of neural networks where there are not one but two neural networks, generator and discriminator. And the role of generator is to take some noise and generate a realistic fake image. And the goal of discriminator is to take an image and kind of identify whether it's a real or a fake. So as you train these two networks together at the right pace, that's very important. They kind of competitively become more and more strong till they achieve the theoretical Nash equilibrium. And at that point, the generator can be used to do some amazing things. So if you have heard of deep fake technology, all these videos, and this is the technique behind that. So we talked about AI, ML, DL. So where does data mining fit in? So data mining is focused on data, is data centric. So it's the process of discovering information from data. And the goal is to discover hidden patterns for actionable insights. And unsurprisingly, it utilizes methods at the intersection of various fields like AI, algorithms, machine learning, statistics, and database systems. High performance computing is the use of parallel processing to run software programs efficiently, reliably, and quickly. So aggregating compute power in a way that you have more processors to work on the same job so that you can get high throughput. It's also known as supercomputing. And it utilizes technologies at the intersection of algorithms, computer architecture, networking, storage, and system software. So these are all the building blocks of what we use in our lab, and we kind of integrate them together. So this AI and high performance data mining is when high performance computing drives your data mining algorithms, which in turn drives big data analytics and accelerates scientific discovery. So in our lab, we routinely take data mining algorithms and scale them up to hundreds or thousands, even tens of thousands of processors so that they can really work on big data. And then, of course, apply them in different domains like materials. So with that brief background, let's go into some real examples. So first, I'll give some examples of AI and high-performance data mining. So one of the most common ways to tackle the big data challenge is HPC, or parallelization. And here I'm showing one example of scalable deep learning, in particular parallelizing the CNN training. So as we know, CNNs or convolutional neural networks are very popular for image data mining. And training these networks is very computer intensive. It can take days or weeks or even more to build a good model. So it's important to be able to parallelize it if possible. Typically, the way this parallelization works is that you have a mini batch that you're training on, so you kind of split it across different processors or different nodes. And so, of course, having a large batch size will improve scalability. So you can use more nodes, and each node has enough data to work on, but it degrades accuracy. So here, if you see, this is an accuracy versus epochs curve. So for a small batch size of 16, you get the best accuracy. So higher the better. And this is a CNN for EDSR model for image super resolution. So you take a low resolution image, and the CNN gives you a high resolution image. So that is the accuracy of that high resolution is measured in terms of peak signal to noise ratio. So so this blue curve is what you get from a batch size of 16. And when you progressively increase the batch size, your performance goes down. So for batch size of 256, the accuracy is significantly worse. So one of our students, Sunwoo Lee, he came up with this idea of adaptive mini batch size adjustment, where it starts with a small batch size and then progressively increases it with some parameters in order to get a good scalability accuracy trade-off. And also, since we are using multiple processors, any parallel algorithm any distributed parallel algorithm will actually need to communicate across processors. So for that, he devised a way to overlap communication and computation. So if you can, it's easy to imagine, it's easy to understand that communication across these processors is actually an overhead. It's because you're waiting for communication to finish before starting the computation again. So he devised a clever way to break down an all reduce operation. For those who may be familiar with MPI programming, there's an MPI all reduce, which by which these processes communicate. So he split that into an all to all and an all gather operation. So he was doing more communication, but then it allowed an overlapping of that communication with computation. So overall, we got high throughput. So here you see one of the examples of the scalability, a strong scaling chart here. So for this EDSR application, you got a speed up of about 81 with 128 nodes. What it means is that the CNN training, which took more than 4 days, we could reduce that to less than 1.5 hours with the same accuracy. So here you see without any loss of accuracy. So this is gray one is the proposed method. So we get the same accuracy as the small batch size run has, but this of course is not scalable, and we can do this much faster now. So more details in this big data paper from last year. And as I said, this is just one example of many data mining algorithms that we have scaled up. There are examples of mining and association rule mining and community detection that we parallelized, and all that software and papers are available on our website. So this is one example of how to tackle big data challenge. Another way to tackle big data challenge is to go deeper. So if we have deeper networks, because the whole promise of deep learning is that because of these deep networks, they have large learning capacity. So how about we just make these networks deeper and deeper? Unfortunately, if we just naively increase the depth, they suffer from this vanishing gradient issue. So here is an example of that. This is an error versus iteration curve now. So the lower is better. And this is the learning curve of a 17-layer neural network on materials data set. And as we increase it to 24 layers, the error actually increases. For 48 layers, it increases even more. So the model becomes worse. And I said that's because of vanishing gradient, because the way these networks are trained, as I mentioned before, the gradient of the error is backpropagated, and to update the weights. And this gradient gets multiplied by very small values at each layer. So if the depth of the network is large, then by the time the gradient reaches the beginning of the network, it almost dies out. So there is no more training. And that's what happens. So a few years ago, this concept of residual learning was introduced in the context of image data mining with CNNs. And one of our students, Dipendra Jha, he recently adapted it for numerical data sets for fully connected networks, where he introduced the idea of individual residual learning. So instead of having the skip connections across a stack of layers, he tried after every layer. And that enabled deeper learning on big data. And here you see, this is the same curve, the 48-layer curve that I show here. This is the same curve. And then with this idea of individual residual learning, we can significantly reduce the error by almost 65%, as you can see in this table as well. So again, more details in this KDD paper from last year, if you are interested. So till now we have looked at two approaches to tackle big data challenge, and now we'll see the application of this in materials science. So first, I want to give some background on how in material science, almost everything depends on these so-called PSPP relationships, and some of you may be familiar with that, but this is very coherent with many other fields like bioinformatics. So here in material science, everything depends on processing structure, property, performance relationships. And in bioinformatics, for example, everything depends on sequence, structure, function relationship. So you have a DNA sequence, you get a coding sequence out of it, and then coding function. And similarly here, we have this PSP relationships where the signs relationships of cause and effect go from left to right. So processing is the cause and structure is the effect. Then structure is the cause and property is the effect. And the engineering relationships of goals and means go from right to left. So if your goal is to get a material with high performance, the means to achieve that goal is to work on the processing and work on the structure and so on. So they are kind of complementary. Interesting thing to note here is that these all these relationships are many to one. So in the processing domain, there can be multiple processing routes which can give rise to the same structure. So, for example, you can when you're processing a material, you can first maybe beat it and then heat it, or vice versa. And there are different ways you can go about processing it, and it is possible that several of those routes give rise to the same material. And then the same property can be achieved by multiple structures or multiple materials. So it is again possible that there are several materials which have the same property. So practically what it means is that the forward problem of the science problem of property prediction, that is, given the material, what the property is, that is relatively easier because there is only one correct answer. But the inverse problem of material discovery. So if I have a property in mind that I want to maximize or minimize, and then I want to discover the materials, there are many possible materials for that. And ideally, you want to be able to identify all of them or most of them. So the inverse problems are much harder, just like any other domain. So materials informatics, which is basically the application of AI in material science, it can generate these forward models for predictive analytics, where we can express the property of a material in terms of the representation. So you can represent the property, you can represent the material as a function of, as by its processing, composition, and structure. And that material as an input can be given to this machine learning model, which can then give you a property. So these AI models are very fast, as we have already seen. And if they're also accurate, which depends on the kind of data it is fed. So if they're accurate, they can also in turn solve the inverse problem of optimization and design. Because inverse models are typically optimization problems. So like maximize the property given some constraints. So it typically needs multiple invocation of the forward model. So think of it as if you had all the resources in the world, and we could just do all the experiments. We'll just make all possible materials, all possible combinations of the elements, 100 or so elements, and there are infinite of combinations of elements. But if we had all the resources, we'll just make all the materials and identify the best for each application. But because we don't have that, if we have a good proxy of an experiment or a simulation, then we can use that in this optimization loop. And it can help us to find the optimal material faster. So all this is, I described this in this perspective articles from a few years ago, if you are interested. So over the last decade, we have been working on several of these projects. So we have different forward PSPP models for property predictions and for inverse PSPP models for optimization discovery, and structure characterization, which is technically an inverse problem, but it has some unique features because of image structure is represented as an image typically. So I listed separately. And in red and green are respectively the publications in computer science and domain venues. So again, an example of how AI and science are, they feed each other to become better and better. So now I'll go through some examples of materials informatics from our lab. So the first example I want to show is LMNet, where we're using deep learning to learn the chemistry of materials. So this is based on simulation data. Some of you may be aware that density functional theory, this is one of very powerful simulations in material science, which takes the structure of a crystalline compound as input and it can churn out some very useful properties by simulation. And of course, it's very slow, and the fact that it requires crystal structure as input makes it harder to use. So over the years, we have developed a lot of models where we take the composition information into the model and the structure information into the model. So for example, if we have a material Fe2O3, ferric oxide, just based on this information that we have 2 atoms of iron and 3 atoms of oxygen, we can calculate a library of attributes like the average atomic mass, the average atomic radius, average electronegativity, and so on. So we can feed in all the periodic table knowledge that we have in representing this material through this vector of numbers. And that can be used as a representation of the material for building models on top of it. Similarly, we can have structure-based models where the local environment around the atom is captured by something like, in this case, Voronoi tessellations. And those numbers like average bond lengths and so on, that information is used to construct the representation. So these are ways to add more and more domain knowledge into the model, which is great, and which we should do whenever possible. But as computer scientists, we were also interested in doing something diametrically opposite. What if we do not give any domain knowledge to the model? So because that's where deep learning excels. Deep learning can work on raw data. So we developed recently this ElemNet model, which works on raw element fractions. So for example, for ferric oxide, it only takes information as input that it has 2 atoms of iron and 3 atoms of oxygen, and it doesn't even know what is iron, what is oxygen. It is just columns. There is no periodic table information whatsoever provided to the model. And then we found that if we give it enough data, we can actually end up with about 20% more accurate models and faster models with deep learning. So here I'm showing 3 curves here. So this top blue curve is a random forest model with elemental fractions. So only raw elemental fractions as input. And then this green curve is again random forest with physical attributes as input. And by physical attributes, I mean this. So when you actually give domain knowledge in terms of handcrafted attributes to the model, of course, the error reduces. So there's a significant difference between this blue and this green curve. But then we found this ElemNet curve, which only takes elemental fractions, no domain knowledge as input. It can beat both these curves at different points. So it can beat the random forest with the atomic fractions as input with only a couple of hundred data points, few hundred data points, and random forest with physical attributes with just a couple of thousand data points. So not only that, we also found that somehow when it is given enough data, it can also learn the chemistry of materials by itself to some degree. So for example, somehow this network knew that lithium, sodium, potassium, cesium, all these are somehow related. Although we did not give any periodic table information to the model, somehow it knew that these are somehow belong together. So it was treating them in a similar way when we analyze the activations of this network. And in a harder test, we try to recover these convex hulls. So some of you may be aware of this. If we have a binary or a ternary system, we can build these convex hulls. So here we are trying to recover this titanium oxide system, which was not present in the training data. And this black curve is the ground truth from DFT, from the simulation. And this brown curve is what we get from ElemNet. And this light green that you see is from this model, random forest with physical attributes, which is all over the place. So there was enough evidence that this model was able to learn the chemistry of materials to some degree. And this is very consistent with other applications and success stories of deep learning. We also have a tool based on this, which can take composition as input and churn out formation energy values. And then we also use this to solve the inverse model because these are very fast models. So we could actually do a combinatorial screening of about 500 million compositions. And then many of these were actually found to be stable. Again, more details in this paper if you want to take a look. The next example I want to show is of deep transfer learning. So typically in material science, we have a problem of small data, not of big data. So what to do when we have small data? So we can use this concept of transfer learning, where we first build a model on big data, which is the same LNet that we built on big data, and then we use that as a starting point for small data. So especially for experimental data, that's very relevant because experimental data is difficult to obtain in material science. So when we did that, we found that compared to training from scratch, so here is this error versus training size. So this is the training from scratch curve, and this is transfer learning curve. So we can get up to 50% reduction in MAE with this transfer learning approach. And then we also found that the final error of the transfer learning model was about 0.07 electron volts per atom. And the error of DFT itself, so DFT is a simulation, it's not ground truth per se. So DFT has an error with respect to experiment, which is about 0.08 electron volts per atom. So it was significant that we could do similar or even slightly better with just a data-based model, AI-based model. Again, more details in this Nature Communication article from last year. This is an example of application of GANs on in material science. So we already looked at what GANs are. So here we are trying to generate microstructure images which are similar to the training data set, and then use it for design. And one of the biggest challenges here for material design is that this is very high dimensional. So this microstructure image is very high dimensional. Even if you have like 100 by 100, so there are 10,000 pixels. So the challenge was to identify a low dimensional representation, which our GAN gives automatically, because GAN starts with a noise vector. In this case, we're using 4x4 matrix. And when it was trained properly, it could take these 16 numbers and give us a microstructure image, which is very similar. So this is these are the original microstructures. These are the generated microstructures. And not only they visually appear similar, they were also found to be statistically similar by 2-point correlation testing and so on. And then when it was combined with the Bayesian optimization loop, we could discover the optimal microstructure for a particular property, a particular optical property, in just about 100 iterations with 17% better property, which actually solves the inverse design problem. And there were some other advantages of this model, that it was scalable. So we can use the exact same generator with a different noise vector to get different dimensions. And all of these are statistically similar to the original set of microstructures. And again, more details in this paper. And I guess this is my final example. Lately, a lot of there has been a lot of interest from industry. A lot of companies have approached us to try to learn and apply these AI techniques in their workflow. And this is one example of our relationship with Toyota. So here we are looking at magnet data. So this is a typical processing workflow. So you have materials samples, and then it goes through a series of processing steps like rapid cooling, molding, hard deformation, and so on. And although it's a very rich processing workflow, because it's experimental, there are a lot of challenges. The data is very small because it's experimental data. It's very costly to generate new data. The data is heterogeneous, so you can have composition information, which is numerical. You can have structure information, which is an image, and it's very noisy. So one of our students, this Jixiang Yang, he built this combination numerical plus image model workflow, where we can take in both the numerical data as well as the structure image data. And because the data is small, we used the same transfer learning idea here by using a pre-trained network VGG16 to extract semantic image vectors from these SEM images, which have nothing to do with this network, which was trained on ImageNet. But because ImageNet is a very big network, it is often found that it has learned all or most of the important features, and it can then work on even images that are very different from the training data. So using that and using some dimensionality reduction, we concatenate these features and then train a gradient boosting regressor on top of it. And we found that we were able to get up less than 5% prediction error for these properties, HCG and BR, which are coercivity and remnants, which are useful, which are the properties that define a magnet. And they were very important because now these forward models can then help realize inverse models, and it can make recommendations, because these industries, they do this at a very large scale. So if a model can make recommendations and uh, identify promising candidates only, so it can avoid higher end processing for unpromising candidates, reduce SCM man hours, reduce the equipment time, and so on, which can result in lots and lots of savings. Which can then also translate into faster magnet design, because now you are spending the resources in the right direction, and you can get to the right material or magnet in this case faster, and also identify the processing routes by process optimization. So again, more details in this paper. So all these examples and more are I discussed this in this recent prospective articles in MRS Communications AI special issue. So if you're interested, you can please take a look at this. Let me see if I have time. Yeah, so let me give a quick demo of some of the tools. So on this website, we have a bunch of software tools. So in the materials domain, we have steel fatigue strength predictor. So here you can put a steel of your choice and get the fatigue strength in real time with quantified uncertainty. So I didn't get a chance to talk much about this, but this is a very important part of any AI model. And I can give a quick example here. So here the prediction is 512 megapascal with this uncertainty. And if I just increase this carbon content to 10%, which is outside the range of the training data, then let's see what happens. So right now it was 512 plus 50 or plus minus 50. And if I make it 10% carbon, it blows up, but so the uncertainty as well. So that tells you that this is not a useful prediction. So any prediction is meaningful only if we have a quantified uncertainty associated with it. So we do that. Similarly, there are other examples of formation edge predictor, and this has the LMNet that I talked about, thermoelectric toolkit, Martin-Site start temperature predictor, photovoltaics, and so on, and other domains as well. So please check it out if you're interested. So I think I'm running short of time, so I will just end with this kind of humoristic. Some people think that AI, machine learning, and big data analytics is like drinking from a fire hose to quench the thirst. And that's not the case, because, and this actually goes back to my earlier example of finding the wrong niche, because can you hear me?
Hello.
Hello?
Yeah,
are you able to
Ankit,
hear me?
actually, we could not hear the last part of your talk. So just like last 1 minute, because there was some network interruption that happened.
Oh, okay. So did you see this?
Yes. Yeah. So we were
Okay.
here.
Yeah. Okay. Yeah. So that's definitely not the case, and this goes back to the wrong needles example that I gave before, because there have been numerous examples of AI gone wrong. It is apparently very easy to learn these techniques and apply, and there are so many pitfalls associated with this that if you apply correctly, you can very easily fall into the trap of wrong needles. And here you see numerous examples, and there are some big players here. So it is very important to learn these techniques thoroughly. It is very tempting. There are a lot of there is a lot of demand for this, and especially to all the students who might be attending this. It can be very to this and take some online course here and there and call yourself a data scientist. But it's very important. Just like any science, it's important to learn it thoroughly and understand the strengths and limitations of the techniques. And if you're working on a real world problem, also understand the strengths and limitations of the data in order to apply it correctly. So with that, I will thank you for your attention and take any questions. Thank you so much.
Thanks, Ankit. Thanks, Dr. Ankit. This was very, very informative also. I liked it very much. We are seeing multiple questions on the Q&A board, so maybe we can have we have time for one question. So one of the question is how good the model is when someone uses the big data to make use of subset of the data and do the training using the subset only.
I see. Yeah, it's a good question. So I think it matters. I mean, it depends on the distributions. So if you have big data, and if you have a good enough sample of it, which captures the distribution of the big data, then you can use that. But if your small sample is skewed, then if you build a model on that small data, it will only work well for that distribution. So that's again, it's quite intuitive if you think about it, but it's one of it's also a common error that when we have big data, it's tempting to just use randomly something, but it's important to ensure that the distributions are preserved, and when you are applying it to the test data, uh, their input distribution should also be preserved. So just like in the steel example I just showed before, when I gave carbon content in the steel which was outside the distribution on which it was trained on, obviously the model will fail. So those are the kind of nuances that we need to keep in mind in order to apply these things correctly. So very relevant questions. Thank you.
Thank you. Thanks, Ankit.
Hi, Ankit. This is Animesh here. Can you hear me?
Yes, I can hear. Please,
yeah, it was a very interesting talk. Thanks for the talk. So I just have one quick question, which was also, I think, asked by one of the attendees. Like, I mean, have you been able to see, like, if the domain knowledge piled up with the deep learning methodologies does even better? Like,
yeah.
So any thoughts on that kind of approaches? Like we have seen in many cases, like if you fuse in certain features towards the end of the deep learning pipeline, this helps sometimes. So any
Yes,
thoughts on
exactly.
that?
Yes, exactly. So yeah, so whenever it is available, we should use it. So the idea of the point of that study was that in many cases it is possible that we do not have any domain knowledge, or it is difficult to quantify it. So can we still apply deep learning in that scenario? And we know that deep learning works well for raw data. So that was what is shown. But as a follow-up to that, which I'm not showing here because of lack of time, we have conducted that study where we use deep networks on the features derived with domain knowledge. And of course, if with careful tuning and architecture search, we can get better performance even with compared to what we should here. So the same network will not work, at least in our case, the exact same network did not work. But when we change the hyperparameters, use more layers and so on, we were able to get better accuracy with domain knowledge and deep learning. So that's very much true.
Thank you. Thanks a lot.
Yeah.
Thanks a lot for accepting our invitation.
Thank you so much.
On behalf of all the organizers. Thanks a lot.
Mm-hmm.
Yeah, so the next talk is by Dr. Satadev Bhattacharjee, and the title for the talk is Modeling Functional Materials Using Data-Driven Methods. So Dr. Satadev Bhattacharjee works as a head of the R&D unit of IKST Bangalore, which is a subsidiary of Korea Institute of Science and Technology, KIST Seoul. He obtained PhD in physics from Ichkar, Kalapakkam and University of Madras, and has expertise in the broad fields of material theory. He uses methods such as first principles based calculations, spin dynamics, Monte Carlo simulations, and to some degree of analytical approach. Machine learning and data analytics are the two toolboxes that he is currently interested in. His current research activity includes simulations of of transport properties of third and fourth semiconductors, surface sciences, electronic, magnetic, and thermoelectric properties of Husserl compounds, permanent magnets, etc. So what I would do is, there is a video which I shall be playing, and then Dr. Satadeep is online, so we'll have a live Q&A with him just after the video.
Good morning, everyone. So, in this brief presentation, I will talk about modeling functional materials using data-driven methods. So here is the outline of my presentation. So I'll make a few words about functional materials, then traditional approaches for modeling such materials, highlighting the density functional theory-based approach. And then I will come to the data mining approach powered by DFT, where people like us are trying to work, the current situation and the challenges that what we see, and then I will come to our recent works on catalysts, photovoltaics, and then I will mention about our recent activities on magnetic materials. So to start with functional materials, so these are the materials which can perform some specific functions under a determined stimulus. So they can have different properties, and they are usually classified in terms of their properties. So these includes like dielectric, magnetic, semiconducting, ferroelectric, etc. And they have ample range of applications from energy generation to healthcare to magnetic memory, sensors, etc. Now, this is the traditional way of simulating functional materials, or usually any materials actually. So there are different, in the left side I show different time and length scale of material simulation. And in the right, I show different methods which are used in those scales, and the properties which are usually obtained using such simulations. So for example, for smallest time and length scales, like quantum scale or atomistic scale, one uses many-body electron structure theory, density functional theory, tide binding approach, etc. And the typical properties which one get are crystal ground state structure, different sort of spectrum such as infrared spectrum, and chemical reactions, other electronics properties, etc. In the higher length scale, one has to do molecular dynamics, Monte Carlo, using classical force field, etc. And the properties such as transport properties, phase equilibrium, etc. can be addressed through such simulation. Now, so the most popular tool in the smallest length and time scale is the density functional theory based approach, and actually in the multi-scale simulation, one uses the results obtained from such method to higher length scale in the bottom-up approach. The results obtained through DFT are often used as the data for the AI-based approaches. DFT has helped us to develop high-performance atomistic calculation frameworks for accurate computing many electronic scale properties of the crystalline solids. So now in this presentation, I will talk about data-driven methods which rely on density functional theory-based calculations. So I will make few words about density functional theory-based calculations. So a solid or molecule in a trivial manner can be thought of composed of negatively charged electrons and ions. Now, since we are talking about very small time scale, one can consider that ions are frozen. So what we need to solve is an electronic system. So in the framework of in the terminology of quantum mechanics, one calls it quantum many-body problem. So traditionally one has to solve this equation known as Schrodinger equation, which was developed in 1920s for this huge number of electrons, and obtain this this many particle wave function. Now this is a very tedious and difficult task because you have many electrons which are interacting, and for the real materials it is very difficult to do such thing. So DFT appeared as a kind of savior where you don't really solve such difficult problem. So this interacting problem is replaced with a kind of non-interacting problem, means you solve for each electron. So basically each electron is in a kind of average field produced by other electrons. And here you solve an equation known as Kohn-Sham equation instead of Schrodinger equation, and all the many particle interaction which we are discussing are dumped into a kind of a potential known as exchange correlation potential. So this approach is quite easy, and this sort of approach is used for making database for materials for the machine learning studies. So this is the typical workflow for a DFT calculation. For the DFT calculation, you start with inputs such as atomic positions, unit cell size, periodic boundary conditions, etc. Then you solve this Kohn-Sham equation in computer, and then you get the properties, which I would like to classify into two categories. One are the fundamental properties such as optimized structure of the system, then electronic band structure, forces, magnetic moment, pressure, etc. By post-processing such properties, you get the other properties which are more technologically relevant, such as electrons mobility, thermal conductivity, etc. Now this sort of DFT calculation has helped to generate many databases. So this high throughput DFT has created many popular databases like Materials Project, the Open Quantum Materials Database, Nomad Repository, etc. But yet the unsupervised deep learning methods are not so popular, because even though we have data, but this database is not so big, and it takes very long time to train the deep learning models, and the interpretability has not developed yet. So usually many people like us, we still use this popular shallow supervised learning, which are shown here, like different sort of regression, clustering, decision trees, random forest, neural network, etc. So in this presentation, I'll show some of the works that which we have done using such shallow supervised learning approach, which can be done with very limited available data. So the first one I would like to show is about something called heterogeneous catalysis. So by catalyst, we mean the material which actually takes part in chemical reactions but do not get used up themselves. So there are different sort of catalysts. The heterogeneous catalysts, homogeneous catalysts, etc. The heterogeneous catalysts are the ones where catalyst is in different state, usually solid, then the reactants and product, usually liquid and gas. So I show you two examples. One is fuel cell, where the reactants are hydrogen and oxygen, which gives the product water, and this process makes electricity, which can be used as a clean source of energy. The catalyst used for such reaction is platinum nanoparticle on carbon black. So this is the solid catalyst. Similarly, another reaction is to get methane from carbon dioxide. So this happens in copper surface, on the top of copper surface, which is again a solid surface, and the reactant and product are in gas. So if you see, this process takes place through formation of different molecules, and these molecules, the interaction between these molecules and the surface is very important, and that is usually described by something called adjustion energy. So in this present work, I will build a machine learning model for prediction of adjustion energies of molecules and atomic spaces on metal surfaces. So we obtain the data from this source known as CMR database. There are two types of data which we get. One is the atomic data, which is the adjustion energy data for the atomic spaces, and another is the adjustion energy data for the diatomic molecule, which contains one oxygen and something else for different metal surfaces. So these are the pictorial view of diatomic molecule and atomic spaces. So we use this scikit-learn package to train different models. And in the right hand side, I show the test RMSE of different models. So here we see that the kernel ridge regression outperforms the other models, and for atomic adsorbate it has RMSE of 0.35 electron volt, and for diatomic adsorbate it's about 0.27 eV. We used elemental features which are shown here. So it's very simple elemental features which we have used. So now, to reduce the number of features, we looked at the feature importance, and we selected 7 important features. Out of them, 3 are adsorbate features and 4 are metal surface features. Now, using this small number of features, we again fit the different models. And what we see is that the scores are almost same as the ones which were done with a large number of features. So therefore, these studies suggest that by using very small number of features, the adjustion energies of monoatomic and diatomic gases can be predicted with reasonable accuracy. Next, we are interested in developing mathematical formulation of adjustion energy in terms of the important features. So for that, we use this method, shear independent screening and sparsifying operators. So we take the following steps. We start with the input feature vector, which is composed of small number of features, 7 features. And then we generate huge pool of features through this set of operations mentioned here. But we generate features which are physically meaningful, not, for example, one which is obtained with adding 2 features with different dimensions. So once we obtain huge number of features, say around 4,500, then we do further feature reduction. We calculate the correlation of these features with the target, rank them up, select the top ones, around 100 maybe, and then use a sparsifying operator to further reduce the dimensionality. Now, using such an approach, we develop mathematical formulation for the adjustion energy in terms of these features. So for atomic adsorbate, we have this formula with RMSE of 0.33, and for diatomic adsorbate, we have the following one, and with RMSE of about 0.18 eV, which is less than even test RMSE, which is obtained by machine learning approach. So this work was published here. So now coming to another work, which is about discovery of new photovoltaic materials from machine learning. So photovoltaic materials are the ones which can directly convert solar energy to electricity we all know about solar cells, which converts um, solar energy to electricity. Now this photovoltaics requires semiconductor material with band gap around 1.4 eV to 1.5 eV for efficient performance. So typically group 3-5 semiconductors like gallium arsenide is considered to be ideal for such purpose. Now in this work we propose a new semiconducting material. In this work we propose new semiconducting materials which are not made yet. So we use the database from this source where AB X2 type of compound semiconductor band gap are reported. This is an experimental paper. And then we do the things which we have done in the previous studies. We fit with different models. We take the simple features. And if you look at the feature importance, we see the volume of the cell is the one which has the most importance. And so what we do is that we make a empirical formula of our target, the band gap with the volume of the cell for the family of the compound which contain nitrogen and the ones which do not contain the nitrogen. Also we obtain a formula of the volume in terms of the other features, and now use these things to search for new materials. So these are the 7 materials which first we choose using the machine learning screening, and then from the DFT we try to verify them also. So from the DFT so this is with band gaps obtained with the simple DFT, and this is with more sophisticated DFT. And also we look at the formability, means whether this compound will be formed or not, also from DFT. So for example, negative values correspond to the one which will definitely be formed. So from this analysis we select this the best candidate as gallium boron phosphide, and we propose this in this paper, and we are hoping that somebody would make it. Now finally coming to some the current activity which we are involved. So this is about Heusler alloys. Heusler alloys are functional magnetic materials which have many applications, and the purpose of this project is, the goal of this project is to find new cobalt based Heusler alloy with high spin polarizations. So we are using 2 databases. One is the DFT database which is created by us, another is kind of online source. And we are collaborating with the experimental group from IIT BHU. So once we find some few candidates, we ask them to try to synthesize them. Now, another work which we are doing is to find out new permanent magnets which are rare earth free. So permanent magnets are the magnetic materials which do not require any, which do not require to be magnetized by some external source. They have their own persistent magnetic field, and they are used in various purposes, like from motors to actuators to waveguides. And the permanent magnets which are the strong permanent magnets are ones which contains the rare earths. For example, this one contains niobium, this one contains samarium, etc. The permanent magnets which are rare earth free are usually weak. So in this project we are searching new permanent magnets which are rare earth free and also strong. So this work is a complete theoretical work at this moment and is in collaboration with IIT Kharagpur. Finally, here are the people who are involved in these projects. Thank you for your
Yeah, so thank you, Dr. Satadi, for your nice talk. We have 1 minute left, so maybe we can have one question at least from the panelists or from the audience. Anyone? Okay, so I can see there is a one question which says that how is DFT different from Hartree-Fock method and how it is similar? Dr. Satadip, am I audible?
Satadip, you are on mute.
Hello.
Yeah, please go ahead. Yeah.
Yeah.
Shwatadip?
Hello.
Hello. Yes, it is.
Hello.
Yeah, yeah. It is now clear. Yes.
You can hear me now.
Yes.
Yeah.
Yes.
Yeah. Okay. So the question is that how DFT is different from Hertrefog method, right?
Yes. Yes.
Yeah. So the Hertrefog method is a kind of web function based method. So it's more costly. So one has to. I mean, usually people don't use it other than uh, molecules and I mean the system where only few electrons are there. So it's a many electron approach, but it is as I mentioned in the talk, it is very costly approach. So usually like helium or some small molecules are studied using Hertrefog approach.
Okay. Okay. Thank you, Dr. Sadadev. Any other question from the panelists? So, Dr. Satadeep, I have one question. So, regarding among all the works that you have presented here, so is the data set available for all these works so that people or the audience here can reproduce the works, and like if they have something novel, they can test on those data sets and the code available?
Yes, those data sets are available online. So I think I have mentioned also where they are available. So yeah, one can download them directly from internet.
Okay, and further, like once we have come up with some kind of model that needs to be tested at lab, right? That's how things needs to be done here.
Yeah. So once you get from the model, you get some physical property, or you say discover some new material, then it has to be tested in a kind of lab, experimental laboratory.
Okay. Okay.
So one question. Sorry, can I ask Mayank one question?
Yes. Yes. Sure. Go ahead.
So one question which people may have is that what you were telling from the beginning, that there is no huge data set as such. So that is a flip side of material science research, that the volume of data set is still not very high. So what can be done to make the volume of data set even more, so that more and more AI researchers can?
Yeah, so making big data sets using experiment is very difficult. So I think DFT can help us. And these days, something called high throughput calculation. I don't know whether Professor Agrawal talked about it. So using that, people are making databases, and these are nowadays. I mean, the databases are becoming bigger and bigger. So I hope within some 5 or 10 years, we will have like the data like what we have in other areas. But I don't think it will be like as big as social science or some business or this thing, but it will be quite large to do something like deep learning this thing. For example, you might have seen, like for example, materials project database has a big I mean, it's one of the biggest database, but there are only few properties which are available, mostly like formation energy and band gap, etc. So one has to actually make big data set for big data sets for some technological properties also, like for example conductivity, electrical conductivity, thermal conductivity, those which actually DFT codes doesn't print actually directly. One has to do some manipulation. So I think that kind of thing will take some longer time. So at this moment, what they do is that they submit some 1,000 or 10,000 jobs together, and it calculates the basic fundamental properties, like for example, bond length, band gap, some energetics, etc. But not the other kind of like complex properties are still not so big. I mean, the database of complex properties are not so big. They are still, I think, for example, thermoelectric data are mostly 800, 900 like that in most of the databases. Entries are less than 1,000 or something like that. but they will grow bigger if really we come we get some if you see some new material is discovered using this approach and which is very useful, then I think people will get a lot of interest and will try to develop more bigger database.
Okay.
That's true.
Okay, thank you, Dr. Satadev. Thanks, and then thanks a lot for accepting our invitation to present the talk here. Thank you.
It is my pleasure actually. Okay. Yeah, thank you.
Okay. So this talk ends our first session on day one, and again we are going to meet at 4 p.m. today. And the second session would be on the physical and the mathematical sciences. Again, we are going to have 4 talks in that session, and the first talk would be by Dr. Max Welling, Learning from Physics for Day Planning. Okay, thank you. Thanks a lot, everyone. So we'll again resume at 4 p.m. today.
Okay, thank you.
Thank you.